So good evening, Konanda. Good evening. So the next chapter, which we said yesterday, that is power system stability analysis. Power system stability analysis. Okay, we wait for 2 or 3 minutes. Still, some people are joining with us. 2 to 3 minutes. We'll wait and we'll start the session. Okay. Yes, I'm really sorry, dear students. Really sorry. Yeah. So I have resumed audio, video, and screen. Yes. Listen. So first of all, we'll discuss some basic concepts of stability here before entering into exact power system stability analysis. Some simple concepts of stability we are going to discuss in the initial stage of analysis. Okay? Yeah. Listen here. Listen. For example, we have one dynamic system here. I'm showing that dynamic system to you like this. Right? Dynamic system. Dynamic system. Or you can call this as a physical system. Physical system means it might be consisting number of elements, storage elements, springs, all these things. Okay, some physical system. Okay, that we have. Dynamic system, or you can say physical system we have. Okay, see, for this dynamic system or physical system, we have some input like this and we have some output like this. Generally, in your control systems terminology, input is going to be denoted as R of t, output is going to be denoted as C of t. Input is denoted as R of t and output is going to be denoted as C of t. Okay, listen here. I am fixing the input to some signal. I am fixing the input to some signal, something like this. So this is a time axis and this is input quantity axis, I can say, right? So that input I am fixing to some signal like this. This is an input signal. Input signal given to the dynamic system. How is output we can expect? How will be the output of this dynamic system? All of you listen here. Very, very simple thing. Very simple thing with what we have started. Yeah, we have taken a dynamic system. We are having some input and we are having some output. Input signal we are fixing to a step input. We are fixing this to a step input. And how will be the output? Means obviously that depends upon the behavior of the dynamic system, we can say. I might expect different types of outputs here. Generally, based on that output, how we are getting, we are going to decide whether our system is stable or unstable. Based on what type of output we are getting, we are going to decide whether the system is stable or unstable. So in that view, in the first case, I have some output signal. I'll show time axis and output axis like this. Okay, so like this I'm showing. Let me copy this one because I have to show these axes for each and every type of output expected. Each and every type of output expected. In some case, I am getting output simply like this constant line. And in some other case, I am showing the output, here. Something like this, I am showing the output. Like this, I am getting the output in some other case. Okay. And in some other case, maybe case number 3, you can say, I am saying that the output signal here, simply something like this. Like this, we are getting the output signal. And in some other case, I am showing that output signal here. Fourth case, that output signal, I am saying it might be happening like this. Okay. And in some other case, maybe the case number 5, that output signal, I am expecting that in this disordered manner, something like this. Yeah, kindly observe my words, what I am saying you. Kindly observe my words. We are fixing the input to this type of signal and I am showing you output in different cases. Case number 1, we are getting this type of output. Case number 2, we are getting this type of output. Case 3, this type. Case 4, case 5. For example, for the given input, what we are talking, if you get output as case 1, can we say system is stable or unstable? Tell me all of you. I need a response from all. Whether the system is stable or unstable. Definitely it will be stable if you are getting an output in this manner. Okay, if you are getting an output like this in the second case, tell me whether the system is stable or unstable in the second case. If you get output as of second case, whether the system is stable or unstable. Stable. In this case also it will be stable, Mridul Sharma. In this case also the system will be stable only. Okay. If you are getting an output like this, third one. What we can say? System is stable or unstable in third case of output. In third case of output, the system will be unstable. Third case of output, we can say the system will be unstable. I'll tell you the reason. Very simple reason only. In fourth case of output, again the system will be stable. Again the system will be stable here. And if you are getting an output like this in the fifth case, we will say the system as unstable. We'll say that the system is unstable. Yeah. What is a simple rule? Listen, all of you. What is a simple rule we are using? We are using to say whether the system is stable or unstable here. What is a simple rule we are using here to say whether the system is stable or unstable? Bounded input, bounded output. Bounded input, bounded output. Means if a system is producing bounded output for a given bounded input, then we are going to say that the system is stable. As far as our understanding is concerned, you consider the bounded output or bounded input means simply it's a step signal right now. If it's a step signal, means if the output becomes constant after some time, then I can say that signal as that output as a bounded output right now. Okay? Yeah. So I will be saying the basic definition of the system stability. System is stable if it gives bounded output for a bounded input. So this is what we'll call generally BIBO stability. We are calling this one as BIBO stability. Bounded input, bounded output stability we are going to say. Okay? All of you understood this statement? This basic statement of stability? Please tell me, I need your response here. Our system, whatever we are going to discuss, power system network, is not at all different from this one. Always we are going to cross check whether we are going to get a bounded output or not for a given bounded input. Based on that, we are going to decide whether our power system network is stable or unstable. Okay, next thing. Bounded means if you are capable to define the output value at any amount of time. At any time, if you are capable to define the output value, we can say that signal as a bounded signal. Okay? Or else, for your easy understanding, you simply take step signal as a bounded signal here. Because the step means it is a constant value for all the time. So as time t tends to infinite, we have a constant signal that we can say as a bounded signal. Yeah, next thing. So let's continue with this further. One small confucius one I want to tell you here before moving ahead with our power system network and all. For example, we have one physical system like this. Okay, so this is a physical system. And this is some input signal we have. Just look here. And this is some output signal we have. I am showing that input signal here. As well as I will be showing you that output signal also here. Input signal and output signal I am going to show. First one, input signal. It is something like this. Input signal. Output signal, I am saying something like this. Input signal is like this, but it's a output signal we have. Tell me now, in this case, whether your system is stable or unstable. Yeah. Tell me, can we say whether the system is stable or unstable? See, actually, we can't make any comment on the system stability in this particular case. Why it is so means, yeah, it is sure to say we are getting bounded output here. There is no doubt about it, bounded output, because it was a step signal, we can say. But how is the input you have here? It's an unbounded input, right? We are unable to define what is the input value with respect to time, exactly speaking. So this particular system, what we are discussing now, it is producing bounded output for a given unbounded input. So we can't make any comment on the system stability. So before studying system stability, the first and foremost one, what you have to confirm is, are you giving bounded input or not? If you give bounded input, then only we should check whether the output is bounded or unbounded. All of you getting my statement, what I'm saying? So in this case, no comment can be made on system stability. So I'm writing here, no comment can be made on system stability, No comment can be made on the system stability. Yeah, fine. Next thing. Let's think about the power system network. As far as our power system network is concerned, this physical system or dynamic system is, I'm going to consider that as synchronous generator right now, right? So I will show in the next slide. So this is one synchronous generator or alternator, you can say simply. Synchronous generator, or you can say alternator. Okay, we are having some input to this alternator, and as well as we are getting some output from the alternator. Yeah, tell me please, what is the input we are giving for this alternator? Mechanical input or mechanical energy input, strictly speaking. So it is a mechanical energy, but I will write this one in the terms of power. Mechanical power input, we can say here on this side. And what the nature of output you are getting for this generator? Electrical output means what? Is it voltage, current, or power? Which one is better word to use now? Power, right? This is one confusion that people will have all the time. Sir, synchronous generator is producing alternating voltage and alternating current. How can I say that as a bounded signal? So as far as this analysis is concerned, we have to consider the output of generator as electrical power. All the way, whatever you discuss in this complete electrical engineering, what you are discussing simply energy transmission and energy transformation. Maybe from one place to other place, or from one form to other form. This is only the thing what we are interested to do in the whole electrical engineering. Okay, so this output, what we are going to get here is electrical power output. I can say electrical power output. Okay, see, sometimes this mechanical power input, what we have here, can also be called as steam input, provided that this generator is a generator existing in a thermal power plant. If you assume that this generator is a thermal power plant generator, I can call this as steam input also sometimes. Steam input. So I will be using the notation throughout our analysis further as PS for mechanical and PE for electrical. PS for mechanical and PE for electrical, I can say. Okay, next. I will be showing that mechanical input signal as well as electrical power output signal right now. Just observe. So this is the axis I am showing. Axis. Mechanical power with respect to time. And here, electrical power with respect to time. I am showing. Yeah, listen. Stop writing. All of you. Stop writing. Just look at this one, what I am saying. Generally, we are going to exert steam onto the turbine, right? We will be exerting steam onto the turbine. And the turbine is getting rotated with the help of that steam force. As a rotor is coupled to the turbine, you can say the rotor is also rotating, and we have the electrical energy output. Okay, see, to regulate that steam input to the turbine, we might be providing one steam valve. I have opened that steam valve up to some extent. In the sense, what you have to expect is, through the steam valve, the steam is forcing onto the turbine at a constant rate. Can we assume? I don't know whether you are following this or not. Can we assume that the force ejected by the steam onto the turbine is constant with respect to time? Yes or no? Why? In the sense, we have opened the steam valve only up to some extent. Okay, maybe half valve position or 3/4 valve position we have fixed. Let us assume. So the steam exerted onto the turbine will be constant with respect to time. Means, can I assume that mechanical input given to the turbine is constant with respect to time? Mechanical power input given to the turbine is constant with respect to time. Yes or no? Yes or no? Yeah? Yeah, I will repeat it again. Vaishnavi, please check. Please check what I am saying. Mubin, please check here. We have opened the steam valve. Okay? Steam is exerted onto the turbine. Continuously steam is exerting onto the turbine with a constant force. Because I am not adjusting the valve further. I am not disturbing the valve further, so that whatever the steam ejected onto the turbine is constant, right? At any time, if you see, same amount of force is going to be applied onto the turbine. Means, can I say that the mechanical input given to the turbine is constant with respect to the time? Have you understood this now, Mubin and remaining people? Have you understood this one? So what we are going to say from this is this mechanical input is going to be modeled as a step signal. It is going to be modeled as a step signal. Okay, so I will show that signal to you. Just observe here. This is the step signal we are showing. This is a mechanical input. Okay, I'll show a little down like this. Yeah, step. Sorry, have a network issue. I'm really sorry. Yeah. Listen here. See, this is a mechanical input. What we have considered here, mechanical input, and this is up to some time. I will say it is T naught. This is up to some time. I can say it is T naught. Up to that time T naught. That mechanical input I am saying as PS naught here. PS naught. And in the similar way, in the electrical output, this is the time T naught we have. T naught. Up to that time, we will be assuming that electrical power output is also constant. Electrical power output is also as a constant signal, something like this. Okay, so this is a electrical output constant signal up to the time T naught. So I'm saying it is P naught. I'm saying that as P naught. Next thing. Listen here. See, can I say the system is stable now? We have a bounded input, so-called mechanical input constant, and we can say electrical output is also constant. So bounded input, bounded output, the system will be stable right now. System will be stable right now. But suddenly, the steam valve was opened little more. Steam valve was opened little more, and it's again constant. Steam valve was opened little more, and it's again constant. In that perspective, this mechanical input what you have here will be suddenly raised to some number, something like this, by some value as delta PS. By some value as delta PS, mechanical input was suddenly raised and it is becoming constant. How is your electrical output now? That's it. Definitely, as a mechanical energy input, you talk in the domain of energy, it will be very clear to you all the time. Energy balance, energy neither created nor destroyed. If you talk in these terms, it will be very, very simple to understand. Mechanical energy input was increased now. What should happen to electrical energy output? Should be increased definitely. Should be increased definitely. Now, can we expect that? This electrical energy output suddenly raised to some number as delta PE like this? Can we expect that? Electrical energy or electrical power output suddenly rises something like that? Can we expect that type of thing? No. Why? In the sense, very, very simple reason I am saying you. Why that electrical energy or power will not suddenly rise to that value of increment what made is we have a storage system here. Synchronous generator means we have a rotor body. There is some kinetic energy stored in the rotor. Yes or no? And as and when we are increasing the mechanical input, all of a sudden, rotor speed will not change. So rotor kinetic energy will not change. Because of that, you don't expect a sudden rise in the electrical energy output at a time. But what you can expect is this electrical power will start rising. And it may make some oscillation, and finally it will become constant if the generator is capable to accept this increment in the steam input what you have made. Okay, so I am expecting that this electrical power might be changing something like this, and it is going to be maintained as constant like that. And finally, you are going to get this like P naught plus delta PE, provided that the system is stable. But it may not be the case always. What we can say, it may not be the case always. Okay, maybe I can say in some other situation of same increment, in some other operating condition of the same increment, this is a PE naught value which is maintained as constant up to the time T naught here, up to the time T naught. Okay, now after making that increment in the mechanical input, what you have done, maybe electrical output is changing unevenly. Means we can't say exactly how much is that electrical power value at a given time. Okay, so in that particular situation, we may make a comment that the system is unstable. Yeah, so I think all of you getting this statement what I have mentioned. Bounded input, bounded output, stable. Bounded input, unbounded output, the system will be unstable. Okay, next thing. Now, on what conditions this system stability will be depending on? After creating the disturbance on the system, whether the system is stable or unstable, who is going to decide it? That we are going to discuss. means factors on which the system will be, system stability will be depending. Yeah. So I am showing in the next slide factors on which system stability depends. System stability depends. Factors on which the system stability will be dependent. Very, very simple factors we are going to discuss here. Very simple factors only. First factor. See, definitely the initial loading condition on the system. How much is the initial power flow in the system, right? What is the initial operating angle of the system? Yeah, please complete it. Please complete it quickly. Soundarya, what I said is, whenever you have a mechanical input rise, something like this, your electrical power may vary like this and it may become constant. That is one option. The other option is that electrical power may vary unevenly also, right? If it is varying like this and becoming constant, we say system is stable. If it is unevenly varying like this, we are going to say the system is unstable. That we have to investigate further. Whether we are going to get an output of case 1 or output of case 2, that we have to investigate. On what factors it will be depending now? On what factors it will be depending? Whether the system is stable or unstable means initial operating condition of the system is one of the things which is definitely deciding the system stability, right? So I'm showing here first factor is initial operating condition. Operating condition is one thing on which the system stability will be depending, or initial power flow in the system, or initial loading on the system. Initial loading on the system. This is one factor on which the system stability will be depending. Second one. Yeah, look here. Second factor I am going to say, the quantity of disturbance. How much disturbance you are giving to the system means how much rise in the mechanical input you are making. For example, in this case, okay, all of a sudden at time T0 you are saying that mechanical input was raised, right? How much quantity you are increasing? Is it low quantity or high quantity? That definitely decides whether the system is stable or unstable. Okay, so quantity of disturbance what we are giving to the system. Quantity of disturbance given. Quantity of disturbance given to the system. This will be definitely affecting the system stability. And one more thing here. Up to how much amount of time this disturbance will exist in the system? Up to how much amount of time this disturbance will be existing in the system? That is also going to decide the system is stable or unstable. Yeah, in our understanding, I will try to explain all these three things by taking some simple power system network. For time being, the third one what I am writing here is time up to which the disturbance will exist in the system. The disturbance will exist in the system. This is also one of the factors on which the system stability will be depending. Time up to which the disturbance will exist in the system. Next thing. Bounded means I said already, Gyaneshwari and anonymous attendee. If you are getting the output as constant, then we can say that signal is a bounded signal. For time being, if you are getting a doubt about the bounded signal in signals and some system and this one, just you assume that if you get a step output, it's a bounded one. Step output right now in the form of energies or power, you are getting step signal. That's a bounded signal you assume for time being for your understanding. Okay, let's move ahead. I am taking one simple power system network here. This is one generator, bus bar, connected to some other bus like this. And we have one more generator here. And this is a other bus. Like this, we have number of buses in the system connected. like this. Yeah. So these are number of buses existing. And this is some load kept at this bus bar. And this is again a load kept at this bus bar. This is again a load kept at this bus bar. Okay. So these are number of buses we have in the system. Buses in the system like this. Right. Next. Listen here. See, disturbance in the sense, what you can expect generally, disturbance. One disturbance already I said, na? One disturbance already I said, mechanical input variation. Mechanical input variation is one of the disturbance what you can experience. Else, better. I'll show in this diagram itself. This is some mechanical input given to the generator, of course, to the system, I can say. This is another mechanical input given to this generator or to the system. Whenever there is a change in the input to the system, definitely we will say that there is a disturbance on the system. The other way of getting disturbance is load variations, changes in the loads. That also definitely causes for a disturbance in the network. Another disturbance is on the network. Another disturbance will be on the network, interconnecting network between input and output. Interconnecting network between input and output. That network also experiences some disturbance, maybe a fault on the system. Maybe a fault on the system. Or you can say simply removal of one line or removal of one transformer. That also we can say as a disturbance on the power network. Okay, so first I'm going to write here what are the different types of disturbances in the system. Types of disturbances. Types of disturbances we can experience. Disturbances we can experience. Okay. Yeah, I'm really sorry. Is it audible now? Audio, video, is it clear now? Yeah. Please kindly confirm. Please kindly confirm. Is it okay now? Yeah. Anonymous attendee, please ask me your doubt in doubt session. I will explain about it, what you have asked me regarding step signal. Yeah, I am really sorry. I'm really sorry. Yeah, fine. So let's continue. Types of disturbances means the first disturbance, what I said, is on the input side, change in the mechanical input. Change in mechanical input to the generator. Mechanical input to generators. This is one thing. Second one we say change in the load. Okay, change in load of the system. Means output, change in the output. Next one we are saying disturbance on the network. Disturbance on the network means we can experience fault on the network, faults on the network. Yes. Fourth one you can say removal of line or removal of transformer. This we are going to call technically as a term contingency. Contingency. In bracket we say removal of lines. These are various types of disturbances which we can experience now. Yeah, fine. These are different types of disturbances we can experience. Next thing. Anyway, I will elaborate these disturbances as we move ahead, strictly speaking. Let's move back to the previous slide which we have shown. We have generators here, network, and we have some number of loads. Okay, very simple question. As we have studied till now many things about fault analysis. Kindly observe here. If I have a short circuit fault, at some point on the transmission line Y, what are the immediate changes we can experience here? What quantities will change generally? Here? Immediate quantity, voltage magnitude will change definitely. Magnitude of voltage will be definitely affected because of this fault occurrence. Next one. What are the other change you can experience? Voltage magnitude is one thing. Of course, currents in the system are going to be changed. See, because of this voltage variation as well as current variation, definitely power flows in the system are going to be changed. See, whenever power flows in the system are getting changed, definitely this electrical power output from this generator might be definitely affected. Repeating the words, kindly observe here. Whenever you have a short circuit fault, voltage magnitudes in the system are changing, current flows in the system are changing, power flows are changing. Whenever power flows are changing, output power of generators might be definitely affected. Whenever output power of generator was definitely affected, we can say frequency of the system is going to be changed. Frequency of system is going to be affected. See, voltage variation in the sense, I expect two types of variations now. One, magnitude of voltage variation. Other one, angle variation also. Rotor angles of the system also going to be affected, we can see. So these are the three basic quantities expected to be changed. Any change you say further, it will be in terms of these three only. You say current variation, voltage is changing, we are saying, right? Definitely current will change. Power variation, as you are saying, voltage and angles are changing, definitely power is going to be changed. Okay, so these are the three basic variations or basic quantities expected to be changed. During disturbances. These are the four basic quantities expected to change. Yeah. Next one. So based on this, we will be classifying the system stability as three types. Number one, voltage stability. Next one, frequency stability. Next one, rotor angular stability of the system. So I can say power system stability now. Power system stability. It is going to be classified into three types. It's going to be classified into three types here. Number one, voltage stability of the system. Voltage stability of the system. Right. Second one, frequency stability of the system. Frequency stability of the system. Next one we are saying as rotor angular stability of the system. Rotor angular stability of the system. Rotor angular stability of the system. Actually, if you study any one of these three stabilities, if you study any one of these three stabilities, it is easy to say whether the system is stable or unstable with respect to remaining two quantities. For example, if I study only frequency stability, I confirmed at the end of my analysis the system is stable with respect to frequency variations, right? Then definitely the system will be stable with respect to voltage variations, and the system will be stable with respect to angle variations also. Okay, and for example, after doing the frequency stability analysis, if I say system is unstable with respect to frequency, then definitely it will be unstable with respect to voltage magnitude as well as the angle. Means if you study any one of these three stabilities, we can confirmly say whether the system is stable or unstable with respect to remaining two quantities. Okay, right. So I am writing the statement in a opposite way. Opposite way means if the system is stable with respect to any one quantity, stable with respect to any one basic quantity, then it will be stable. It will be stable with respect to remaining two quantities. Remaining two quantities. Remaining two quantities. If it is stable with respect to any one quantity, then it will be stable definitely with respect to remaining two quantities, what we are seeing. Clear? Next. See, as far as our syllabus is concerned, of course, with respect to examination also, we have this topic in our syllabus, that is rotor angular stability. So I will be continuing only with respect to this one from this point onwards, so-called rotor angular stability of the system. Rotor angular stability of system. Anyhow, before discussing about that rotor angular stability and all, first I want to know what is aim of doing the stability analysis. Already we discussed the fault analysis, where we said the aim of doing fault analysis is selecting the relay setting, means selecting the pickup current of relay, and designing the breaker rating or selecting the circuit breaker rating. These things we have done in the fault analysis. In the similar way, what is the aim of doing this stability analysis theoretically? Okay, that we have to discuss first. Later on, we will extend this rotor angular stability analysis further. Yeah, so let's take in the next slide. Next slide. What is the aim of doing the stability analysis? Aim of stability analysis. Aim of doing the stability analysis. Yeah, look here. First aim of doing the stability analysis is security assessment or security check, you can say. Security assessment. Very simple word to understand. Don't complicate that word by looking at that term security. Very simple. See, when the disturbance is going to come onto the system, we don't know. When we are going to get fault on the system, when we are going to get some failure of equipment in the system, that we don't know and we can't expect also at all. But before that to be happened in the system, before that happens in the practical system, first we should know that if it is happened, if that is happened in the system, whether the system will accept it or not, whether the system will be remains the stable mode or not after taking up that disturbance. That we have to know, right? That we have to know. That we are calling as security assessment here. Is how far our power system network is secured with respect to disturbances. What is the preparation level? What is the preparation level of the system of accepting the disturbances? Of accepting the disturbances. That is one of the aim of the system stability analysis, which we are saying as security assessment. Okay, very simple, very simple. I am writing the statement. Kindly go through it to check the preparation level of system, preparation level of system in accepting disturbances, accepting disturbances. Okay, to check the preparation level of the system in accepting the disturbances. This is we are going to call as security assessment or security analysis. Okay, next one we are going to say reliability check. Reliability check. What do you mean by this reliability? Reliability in the sense simply whether the load is going to be supplied or not within a duration of time. For how much amount of time you say confidently that the load is going to be supplied. For example, in a particular day, how many power cuts you have? What is the least possibility of getting the power cut? If you don't have power cut, I believe that my system is stable. I believe that my system is well reliable. So, for example, as we are doing our class now, with a good lighting and good AC, right? If power cut occurs, obviously we will say that reliability of our electrical system will be less. That we can't continue the class in that manner, right? Like we say, internet problem. So how far I can confidently say that my internet is working properly to continue the class? This point we are going to say as a reliability check here. Okay, so simply reliability check in the sense it is the confidence level of system, right, to satisfy the load. Requirement. It is a confidence level of the system to satisfy the load requirement. This one. Next one, kindly understand. Next one, listen please. I am going to the previous slides to say this one. This is one power network we have taken, and this is a place of fault. And already you know that we will be keeping circuit breakers associating relays here. Protective devices we are keeping on both sides of this line. Very simple. Try to understand now. Fault occurred at some point on transmission line. And we are getting some fault current supply from this side, as well as we are getting fault current from the other side also. This side we are having the fault current flow, and this side also we have the fault current flow. Next thing what I am asking is, listen. How much time this relay and circuit breaker combination, means protective switchgear, will take to remove the faulted part of the network? How much time it will take to remove the faulted part of the network? This is one of the factors which definitely decides the system stability, which we said as time up to which the disturbance may exist in the system. Definitely decide the system stability. For example, I will say in a simple word, after the fault occurrence, protective switchgear acted very quickly to disconnect the faulted part of network. Then I can say the system may be stable. But if the protective switchgear taken a long amount of time to clear the fault, then we can say the system may not be stable. Within how much amount of time? The faulted part of network or fault must be cleared from network. Within how much amount of time the fault must be cleared from the network? That we are going to call as critical clearing time. Critical clearing time to make sure that the system is stable. To calculate the critical clearing time, we are going to do the stability analysis here on the paper. Okay, so I can say the next aim here is to find critical clearing time. Critical clearing time. So I will show in bracket TCR. Critical clearing time, TCR. So it is a time. It is the time before which the fault must be cleared. Fault must be cleared. Fault must be cleared to make sure that the system is stable. To make sure that the system is stable. System as stable. Okay. It is a time before which the fault has to be cleared to make sure that the system is stable. Fine. So this is the aim of doing the stability analysis, basically speaking. So next we will be moving on to rotor angular stability of system. And in that rotor angular stability of system, first and foremost thing I am going to discuss here is single machine connected to infinite bus bar. Means we have a single synchronous generator, alternator connected to infinite bus bar that we are going to discuss next. Yeah, let's say single machine connected to infinite bus is the next heading. Single machine connected to infinite bus. Single machine connected to infinite bus. Shortly, we are going to name it as SMIB. SMIB. Single machine connected to infinite bus. So in bracket, I am saying as SMIB. Okay, listen here, listen. See, this is one synchronous generator we have. Synchronous generator having some mechanical input. Having some mechanical input named as PS, I can say. The electrical output I am showing as P. Electrical output I am saying is P. For your understanding only I am saying this. For your understanding only. This generator having a rating of let's say 100 megawatt. For your understanding only I have taken that rating. Don't write the rating in your notes. Don't write the rating in your notes. It's a 100 megawatt generator. 100 megawatt generator. To what we are connecting this one? After designing the generator, to what we have to connect this one? To Indian Power System Network. Yes or no? So this is connected to our Indian Power System Network. Indian Power System Network. What is the power rating of the Indian Power System Network? Tell me anybody. What's the power rating of the Indian Power System Network? Maybe 360 gigawatts. The rating of that Indian Power System Network is 360 gigawatts. Right. So what is the generator rating? What we are connecting to that? 100 mega. 100 mega means you can write this one 0.1 gigawatt. You can write it as 0.1 gigawatt. See, whenever you are putting that 0.1 gigawatt into the 360 gigawatt system, whether the system will experience any change, whether the Indian Power System Network will it going to experience any change? Yes or no? No, it's not going to experience any change at all. Because the power rating of already existing system itself is very, very large value. Even you connect that 100 megawatt generator to that or remove that, it makes no change in the system operation. System operation. This we have to understand first. Okay, now this is a bus. This is a bus for which we are connecting this one, connecting this small generator, right? And this is a bus corresponding to that Indian Power System Network. See, listen. Look all of you. With respect to this bus, where we are standing, red color bus, if you try to replace this whole Indian Power System Network, into a single voltage source in series with impedance manner, Thevenin equivalent. If you want to represent this whole Indian Power System Network in its Thevenin equivalent model, we can expect we can expect that Thevenin equivalent impedance may come very close to 0. Thevenin equivalent impedance may come very, very close to 0, means this bus bar might act as ideal AC voltage source with 0 internal impedance. 0 internal impedance, which we are going to name as infinite bus bar. Infinite bus bar. Else, listen here, else. You can understand in this way also. This is a bus bar having a voltage mod V and operating at a frequency F. If you disconnect this generator, disconnect the 100 megawatt generator, do you have any change in this voltage and change in this frequency? Tell me please. Yes or no? After disconnecting that small generator, do you have any change in the operating voltage and frequency of that bus bar? Not at all. And you connect it. Do you have any change in that voltage and frequency of the bus bar? No. So this is a bus which is going to maintain constant voltage and frequency irrespective of connection and disconnection what we are making here. Means irrespective of disturbances what we are making here. This bus we are going to treat as infinite bus. That bus we are going to treat as infinite bus. So I'm going to show this as simply a single generator connected to infinite bus bar. Infinite bus bar, and this is the mechanical input to this generator, and this is injecting some electrical output into that infinite bus bar. And this infinite bus bar, it acts as ideal AC voltage source. Will be acting as ideal AC voltage source. Okay. See, this generator might have some internal voltage. I'm showing that here. Else, I will draw the equivalent circuit better. I will draw the equivalent circuit for the better understanding. This generator, what we are discussing now, is going to be represented as voltage source in series with the impedance like this. This is a generator on which we are doing stability analysis actually. It is a generator on which we are doing the stability analysis. And this impedance of generator you call as JXS. Impedance of generator is JXS. And this is mod E voltage magnitude at an angle delta. I will explain about the delta very clearly. Mod E at an angle delta I am showing. And this is a bus bar, so-called infinite bus bar. How that infinite bus was modeled in the equivalent circuit, we said simple AC voltage source without any internal impedance. So this is going to be modeled as simple AC voltage source like this. And this voltage, so-called the infinite bus voltage, I will be treating as reference. That bus voltage, I will be treating as reference. It will also act as generator. Mod V at an angle 0 degree I am considering. Ideal AC voltage source means we don't have any internal impedance at all. We have only voltage source. I think already I have discussed about this infinite bus in the fault analysis. Yes or no? Next thing. See, this is the electrical power injected. That's the electrical power injected. I want to find out formula for that electrical power injection. Okay. So if you are familiar with this formula, I will write it directly. It will come like mod E into mod V by XS into sine of delta minus 0. Like that you will get. Mod E into mod V by XS into sine of delta minus 0. Else. Very simple. This bus voltage is mod V at an angle 0 degree you have. You find out this current I. After getting that current, you take up that V into I conjugate as a complex power injection into the infinite bus. From that one, you pick up the real part. Clear? So I'm writing that equation little. Complex power injected into infinite bus. Injected into infinite bus. S is equals to simply V into I conjugate. Okay, V, I'll say. What is that I here? I is nothing but mod E at an angle delta minus mod V at an angle 0 by JXS. Mod E at an angle delta minus mod V at an angle 0 by JXS. Na? JXS, you write it as XS at an angle 90 degrees. And this V, you can replace it as mod V at an angle 0. And for this current, you have to apply the conjugate. For the current, you have to apply the conjugate. Okay, you extend this one if you want. You extend this one if you want further. And this SE, we can write it as real power plus J times of reactive power. Real power plus J times of reactive power. From that, you can get the real power injection, real power expression, PE is equals to mod E into mod V by XS into sine delta. Like this, we are going to get the expression for the real power injection. Real power injection. Mod E into mod V by XS into sine delta. Real power flow from generator to infinite bus. Generator to infinite bus. Okay, next thing. Listen, please. So I'm taking up in the next slide. Taking up in the next slide. Just have a look. See, already we discussed a little about synchronous machine in sequence networks. Particularly in the sequence networks of generator, we have discussed something, right? We have discussed something about generator. Sorry, generator, D axis, Q axis, all these things we have discussed. Sir, what if V does not have angle 0? I will come to that, Pujan. That's what I am discussing now. Look here, look here. See, generally, first I'll say, this is a generator on which we are doing our study. Generator. And infinite bus bar, what we have now, that can also be a synchronous machine only, right? Infinite bus bar is also a synchronous machine. Definitely, because it's a AC voltage source. So I can say this is the infinite machine. Infinite machine. How many number of machines we have in the system now? How many number of machines we have in the system? 2 machines. 2 machines. One is a generator on which we are doing stability analysis. Other one is an infinite machine which we have taken. Infinite machine, how you get means, with respect to the bus bar, you converted the whole network into the Thevenin equivalent model. We get only voltage source, no internal impedance. That we are saying as infinite machine equivalent. Infinite machine equivalent. Okay, next. This generator internal voltage is mod E at an angle delta. This infinite machine internal voltage is mod V at an angle 0. Mod V at an angle 0. Okay. Next. See, first I'll take it is number 1 better. It is number 2. Number 1, number 2. First machine I am discussing first. First machine. It has some direct axis and quadrature axis. Machine number 1 will have some direct axis and quadrature axis of the rotor that I am showing. This is the direct axis of the machine number 1. Direct axis of machine number 1. D1 I will call it. And it is a quadrature axis of the machine number 1. Direct axis of machine 1. And this was quadrature axis of the machine 1. D1 Q1 axis. Fine. Look here all of you. Whatever the flux produced by machine 1, rotor of the machine 1 will be along with its own direct axis. So I can say flux produced by machine 1 will be along this line simply. This is the flux produced by machine number 1 rotor. Flux produced by machine number 1 rotor. How is the induced EMF in the stator of machine 1 with respect to this flux? How is the induced EMF? Induced EMF in this machine stator? Please tell me. That will be lagged by an angle of 90 degree. Lagged by an angle of 90 degree means I can say that that induced EMF might be in this manner. This is the induced EMF in the machine number 1, E. Induced EMF in the machine number 1, that is E. Okay, next thing. See, actually, machine 2 having a voltage mod V mod V. And there is an angle difference between E and V. Between E and V, we said it is delta. Delta is an angular difference between these two. Okay, so because of that angular difference, I will be showing that voltage V something like this. This is the infinite bus voltage. Infinite bus voltage. In fact, you observe that this phasor diagram is rotating in anti-clockwise direction. It is rotating in the anti-clockwise direction in the sense this V what we have, V voltage, infinite bus voltage is in lagging with respect to internal voltage of the generator. So that's why I have shown this E in lag with respect to E. By how much angle? Delta. How much angle is that? Delta. Okay, listen. Next thing. Look all of you. Can I call this V infinite bus voltage as induced EMF of machine 2? I need your response. Can we call this V, so-called infinite bus voltage, as induced EMF in the machine 2? Induced EMF in the machine 2. Yes or no? Tell me yes or no? Can we call that infinite bus voltage as induced EMF in the machine 2? Yes, we can call it. Okay. After calling that, can I say this V is nothing but the axis of V is nothing but quadrature axis of machine 2. Can we call this as quadrature axis of machine 2? Yes or no? Yes, we can call this itself as quadrature axis of machine 2. Quadrature axis of the machine number 2. Yeah, that's what I am saying. We have the induced EMF along the Q axis of machine 1. We have the induced EMF along the Q axis of machine 1. So definitely, second machine will have its induced EMF along the Q axis of that, means Q2. Okay. How will be the direct axis of machine 2 now? How will be the direct axis of machine 2? Tell me please. It will be 90 degree with respect to Q2, right? 90 degree with respect to Q2 means I can expect that the direct axis of machine 2 might be something like this. Something like this we can experience direct axis of machine 2. So I think all of you clear about this now. This is the direct axis of machine 2. Direct axis of machine 2 means rotor flux of machine 2 will be along this D2 axis. Rotor flux of machine 2 will be along this D2 axis. So this may be the line of that second machine rotor flux, which you can say as phi. Now, very simple question. The angle between Q1, Q2 axis, Q axis of both machines is delta. Then what will be the angle between the two D axis now? D1 axis and D2 axis. What is the angular difference between these two? That will be also delta only, right? This angle will be again delta, we have to say. That angle will be again delta. Clear? Next thing. How V is lagging with respect to E means that's what you have taken earlier, right? Because we have the power flow from the generator to infinite bus. So because of that, we are saying by taking that voltage V as reference, we will feel that generator voltage will be in leading. Okay, now listen. For example, you assume the rotors of the first machine and second machine as salient pole. So if you draw those rotors here, first machine rotor I am showing, first machine rotor might be something like this. Getting this, please? You should observe this in a sequence actually. This is a rotor of the first machine, we can say. Salient pole rotor we are taking just for the easiness in the understanding. So this is a rotor of the machine number 1. How is the machine number 2 rotor? Machine number 2 rotor will be along the direct axis of this machine. So this will be the machine 2 rotor. Machine 2 rotor, something like this. Okay, so this is the machine 2 rotor. Yeah. Could you please tell me now, what is delta here exactly? What is the delta here exactly? Tell me. How delta? That's what I said. Anonymous attendee. Go through it. Go through it, please. Between Q axis, if you have an angle of delta, obviously between direct axis also you'll have the same angle, right? Yes. Tell me, please. What is the delta now? Angular difference between the two rotors in the system. That's what we say generally, rotor angular difference. Rotor angular difference. But it's an electrical angle. It's an electrical angle. Okay? Because number of poles in machine 1 and machine 2 might be different. But all the rotors are scaled onto 2 pole. All the rotors are scaled onto 2 pole. And then we are saying this as electrical angle. Electrical angle. Right. So delta is rotor angular difference. Rotor angular difference between rotors. Difference. Rotor angular difference. Clear? Yes. Next thing. So what you have to understand again, here is this phasor diagram, what I have drawn here, it is continuously rotating. Is continuously rotating. In which direction you can say? In which direction? Anti-clockwise direction. This phasor diagram will be continuously rotating in the anti-clockwise direction. So just for your understanding sake, I am showing that here, and it will be continuously rotating in this direction. In this direction, it will be rotating continuously. And you know, both rotors are rotating at same speed. For example, if both rotors are rotating at same speed, maybe synchronous speed, if you feel, rotor 1 and rotor 2, both are rotating at synchronous speed, means definitely this angular difference between the two rotors, so-called delta, it is going to be maintained as constant. Delta is going to be maintained as constant. Please kindly listen my words. Please kindly listen my words. If both rotors having same speed, both rotors have same speed, then what you can say? Delta is constant. Yes or no? Delta will be constant with respect to time. Delta will be constant with respect to time. Yeah, please listen again. If delta is constant with respect to time, what you can say now? If delta is constant with respect to time, what you can say now? Anybody? Electrical power, what we have derived now, EV by Xs into sine delta. EV by Xs into sine delta. So electrical power output is constant with respect to time. Delta is constant with respect to time means electrical power output also constant with respect to time. Na? For a given mechanical input, electrical power output is constant, means we can say the output is a bounded signal. Output is a bounded signal. So definitely we can say that the system will be stable. System will be stable. Okay. So that implies electrical power output is also constant. Electrical power output is also constant. I think all of you getting my words. Yeah, what is zero, Jayant? You said me zero. What is that zero? Yes, I think some of you at least have understood what is the meaning of this delta exactly. What reference should we take delta in both? Actually, anonymous attendee, that's your wish now. What you want to consider as reference? Is it infinite machine or your generator? What you want to take as reference? Yeah? What you want to take reference? For example, if you take your infinite bus as reference, obviously your generator rotor will be leading by an angle of delta, right? It's rotating in anti-clockwise. Which rotor is ahead? Which rotor is first for you? Obviously, generator rotor is first. Later on, the infinite machine rotor is following. Right? Infinite machine rotor is in lagging with respect to the generator rotor. So if you consider infinite machine rotor at an angle 0 degree, your generator rotor will stay at an angle of delta. At an angle delta. For example, if you say that your generator rotor is at an angle 0 degree as a reference, your infinite machine rotor will be lagging by an angle of delta, means you have to keep minus delta for that. Right? But for analysis sake, we used to consider infinite bus voltage or infinite bus rotor as reference. Based on that, we measure the angle of any other rotor. So I think all of you getting this. I think I can move ahead. Electrical angle only. Alan, this delta is an electrical angle only. Next thing. See, whenever you create some disturbance on this network, one more word, kindly listen. Whenever you create some disturbance on this network, rotor speeds are going to be changed. That's what the expectation. Rotor speeds are going to be changed. Sir, meaning of rotor angle constant means both rotors. Yeah, see, analysis certainty. If rotors are rotating, look here, please. Look here. If rotors are rotating at the synchronous speed means, can I say both rotors are inclined on each other? No. The angle between two rotors are constant. That does not mean that both rotors are coinciding together. Both rotors are not coinciding together. Rotor angular difference is there and rotor is continuously rotating. That's the two rotors are continuously rotating. That is the meaning. Those two rotors will not fall onto the same axis. If those two rotors are fall onto the same axis, angle difference is 0, then electrical power output will be definitely falling down to 0. Yeah, next. Let's move ahead, please. Tell me, what is frequency of the infinite bus? All of you, I need your response. Kindly tell me. What is the infinite bus frequency? Frequency of the infinite bus. Constant. Frequency of the infinite bus is constant. What is the meaning of that now? Frequency of the infinite bus is constant. The meaning is, listen here. The meaning is, the frequency of this induced EMF is constant. The frequency of this induced EMF is constant means this infinite machine rotor will always rotate at synchronous speed. Infinite machine rotor will always rotate at the synchronous speed. Okay, so this second rotor, red color one, what I said here, it will be always rotating at synchronous speed only. But whenever you create some disturbance on the network, infinite machine rotor speed will not change. But the rotor speed of generator may be changed. Whenever the rotor speed of this generator is getting changed, if that is not equals to synchronous speed, then what will happen to delta value? Anybody please tell me. What will happen to delta value? Definitely changes. Delta value will be definitely changing. Clear? Right. Because of this delta change, definitely we expect that there is a variation in the electrical power. How that variation is? If that electrical power is changing with respect to delta, after some time, if this generator rotor speed comes back to synchronous, then delta will be constant further. If delta is constant, electrical power output is constant, then we can say that the system will be stable. Yeah. I don't know whether you have understood this simple concept or not. You want me to repeat? This one? Please tell me. Yeah. I am repeating this. Kindly observe. I will write and repeat it. If disturbance occurs, speed of generator changes. generator changes, but infinite machine speed is constant. Infinite machine speed is constant. Okay, next. Whenever speed of generator is changing, that implies delta will vary. Delta will vary. If delta is varying, obviously electrical power PE also changes. Also changes. This is during the disturbance. If speed of generator reaches to synchronous speed after reaching to steady state. After reaching to steady state, if the speed of generator reaches back to synchronous speed, if speed of generator reaches back to synchronous speed, then delta will become constant. Delta will become constant. That implies PE becomes constant. That implies system will be stable. System will be stable. So I think all of you getting this. System will be stable. Okay. And after creating the disturbance, what you said, after creating the disturbance, if speed of generator does not reach to synchronous, if the speed of generator does not reaches to synchronous, what you can expect? What you can expect now? Delta will be continuously changing with respect to time. Delta will be continuously changing with respect to time. And electrical power also changing continuously with respect to time. Then we are not getting a bounded output. If we are not getting bounded output, system will be unstable. System will be unstable. Are you clear? Simple. Disturbance in machine 1 means that means disturbance occurs in machine 1. Okay, disturbance is affecting machine 1. You say better. Ankur Kashyap, you say that machine 1 is affected by the disturbance, not the machine. How much time required to back synchronous speed and all that we have to investigate, right? We don't know about it. Yeah. Next, let's move ahead. Tell me, after creating the disturbance, what you are talking now, after creating the disturbance, you know this omega is changing and delta is changing. According to that, electrical power is also changing. How much change in the speed you are going to get? How much change in the delta you are going to get? That is going to be decided by magnitude of disturbance what you are creating, or you can say quantity of disturbance what you are creating. If it's a small disturbance, change in the omega is very less, delta variation is also very less. If the disturbance is severe, large quantity of disturbance, you say change in the speed is high, the angle variation is also very high. So in the view of study, or for the purpose of study, I am going to classify basically disturbances of two types. One is of small magnitude, second one is of large magnitude. By the way, I will say we have to study two types of stability analysis. One is for small disturbances, next one is for large disturbances. Okay, so I'm saying further, two types of rotor angular stability analysis we have. Two types of rotor angular stability analysis. Two types of rotor angular stability analysis. Stability analysis. First one we are saying small disturbance stability study. Small disturbance stability study. And second one is a large disturbance stability study. Large disturbance stability study. Large disturbance stability study. Small disturbance stability study. And the next one we are saying is large disturbance stability study. Yeah. Next thing. Next. Very simple thing I am saying. See, whenever you have this type of small disturbance in the sense what? A small power variation, maybe a small load variation, right? That you can say. Okay, you can say this one as a small load variation. Small load variation, we can treat as a small disturbance study. What do you mean by large disturbance? Maybe sudden and large variations in load, input power of generator, and you can say fault on system. All these things can be coming under the large disturbance stability study. Okay, next. See, whenever you have this small disturbance, already I said omega variation is very less. Omega variation is very low. Very low. Delta variation also very low, you can say. Delta variation also very low. Delta variation is also very low. But for large disturbances, as we said, omega variation is very high. Omega variation is very high. Very high. And obviously, you can say delta variation is also very high. Delta variation is also very high, you can see. Delta variation is very high. Okay, next thing. Next thing. See, whenever that delta variation is very, very low, you are saying. Delta variation is very, very less, you are saying. In mathematical analysis way, I am saying, mathematical analysis way, it is not required to study exactly how the delta is changing with respect to time. You no need to study how the delta is going to change with respect to time. Try to tell whether the system is stable or unstable. That will be sufficient in the first case. In the first case, as a delta variation is very low, you no need to study how the delta is going to change with respect to time. Just to tell me whether the system is stable or unstable. But in the second case, as a delta variation is very high, definitely you should know or you should study how the delta is going to change with respect to time. Based on that only, we have to say whether the system is stable or unstable. Okay. So in the first case, I'll write. It may not be required to study. It may not be required to study delta versus time. It may not be required to study that delta versus time. But how to say whether the system is stable or unstable? How to say whether the system is stable or unstable for small disturbances means just by using the power equations. Maybe real power equation we'll use. Based on that only we are going to confirm whether the system is stable or unstable, right? And this small disturbance stability can be done by power equations. Power equations. Okay, but here in this case, delta versus time must be studied. In this case, must be studied. So delta versus time must be studied in the sense definitely sir. So to make delta 90 degree, we need to have disturbance, right? Why you are asking that type of question, Anand certainly? To make delta equals 90, we need to have disturbance. What is the thought? I don't know. Yeah. Why that 90 degree is coming here? Have we discussed anything about 90 degree here? Listen here. Delta versus time must be studied. And to study that one, definitely we should think about the rotor mechanical equations. So this analysis can be done by done by rotor mechanical equations. Rotor mechanical equations. This analysis has to be done by rotor mechanical equations. Okay, next thing. I will ask one very simple question here. I will ask one very simple question here. Just listen to me. What do you mean by steady state operation of power system network? What do you mean by steady state operation of the power system network? I will give some options. To you. Option A. The power generation and load demand exactly constant with respect to time and are equal. Steady state operation means what? That's the question. Option A, power generation, load demand are exactly equal and these are constant with respect to time. Option B, there is a continuous and small variations in the load as well as in the power generation. That is option B. Option C, there is a continuous large variations in the power demand as well as the generation. Tell me, all of you, which one is going to be called as steady state operation among the three? Is it option A, option B, option C? See, for example, listen here. For example, if we switch off some light or fan, maybe in this room, is it going to show any effect on Indian power system network? If you switch off some load, or if you switch on some load, is it going to show any effect on Indian power system network? Why can't it be? The load what we are operating here inside your house connected to the nearby distribution transformer. That distribution transformer is connected to some substation. That substation is connected to some grid. Definitely, whatever the load changes you are making, maybe switching off, switching on of equipment inside your house, sir. Definitely, these are nothing but disturbances on the power network. Disturbance on the power network. Following up means, can I say now, in the steady state operation of power system network, always the power system network will experience small and continuous variations of load as well as the generation. Can we say this type of statement or not? Yes or no? Yeah, nobody answering. Yes. So steady state operation basic definition itself is there is a continuous variation in the load as well as generation. Means we will say under steady state operation, always the system is operated with a small disturbances only. That's why in some cases, the small disturbance stability can also be called as steady state stability of the system. Small disturbance stability analysis can also be called as steady state stability analysis of the system. Clear to me? Is it clear? Steady state stability analysis of the system. Okay, next. Large disturbances when we are going to get, if you have a fault, that thing. So I can say it's a transient. So large disturbance stability can also be called as transient stability of the system. Transient stability of the system, we can say. Large disturbance stability can also be called as transient stability of the system. Okay. So first we will continue with the steady state stability of system. Next we are going to continue with the transient stability of the system. Anyhow, before moving to any one of these two, either steady state or transient, first I want to give you what is the textbook definition for the system stability here. Power system stability definition I want to discuss. Yeah. So I am showing in the next slide definition of system stability. Definition of system stability. Definition of system stability. Okay. Yeah. Just go through it. Go through the definition here. So it is a capability of synchronous machine It is a capability of synchronous machine, maybe generator or motor, whatever it is, synchronous machine, to be remains in synchronism or in stable mode, to be remains in synchronism or in stable mode with respect to what? The external connected network. External connected network may be a big power system, you can say. External connected network or infinite bus is a better term to use generally. Infinite bus, or sometimes you say tie line, right? In stable mode with respect to external connected network or infinite bus or tie line, even after experiencing a disturbance. Even after experiencing a physical disturbance. A physical disturbance. Right? So this is the basic definition of the system stability. Okay. So next we will be continuing with steady state stability analysis. Steady state stability analysis. Next heading I will be taking. Yeah. Next heading is steady state stability analysis. Steady state stability analysis. See, definition of the steady state stability of system will be same as this. Definition of the steady state stability of the system will be same as this one. But only one change is that at the end you said a physical disturbance, right? In place of that, you have to write a small physical disturbance. Small physical disturbance. I think you don't need to write that whole statement. Just to say at the end you have to write a small physical disturbance. Small physical disturbance. It's a capability of synchronous machine to be remains in synchronism or in the stable mode, even after experiencing a small disturbance with respect to external connected network. Yeah, I'll come to that tie line discussion later. Tie line, somebody is asking me. I will discuss that doubt later. Next thing. So I'll say a two machine system here, basically in this steady state stability analysis. I'm taking up one two machine system. Two machine system. First machine I will choose as generator. Second machine I will choose as motor. In earlier case, we have taken a finite machine generator and we have taken that as infinite machine. Sir, can the synchronous machine rotate at speeds other than synchronous speed? Why can't it be? You are providing prime mover. Whenever you have a disturbance, speed will not be equal to synchronous speed, right? Why can't it rotate it other than synchronous speed? Yeah. Synchronous machine means always synchronous speed. Is it the thing we have studied? Then it is wrong, definitely. So with how much speed you rotate, based on that, the rotor will rotate. Yes or no? Right. Look here. So I am showing two machines here. One is a generator, other one is a motor. Both are synchronous machines only. Synchronous generator, synchronous motor I am considering now. This is one synchronous generator. And this generator is having some internal reactors. Resistances of network was neglected completely. Okay. So this is mechanical input. To this machine, I am saying it as PS1. electrical output I am showing as PE1. This machine is having some internal reactance. Let us say Xg. Xg is a internal reactance of that machine. Next thing. You have transmission line wire. The transmission line wire is having some reactance of XL. Reactance of XL. And at the end of this one, you have a synchronous motor, let us say. That motor might have some internal voltage along with its reactance XM. And this is a motor shaft delivering some mechanical input PS2. Okay. And having some electrical input to this motor as PE2. So then in that case, frequency will not be 50 Hz. That's the problem what we are facing now. That's the problem what we are facing. That's the reason why we are studying this stability analysis and all, right? Okay. Else you can say in this transmission line wire, electrical power flow, you say simply PE. Electrical power flow, you can say it is simply PE. Okay, next thing. Generator internal voltage, I am showing as EG at an angle of delta G. Motor internal voltage, I am showing as EM at an angle of delta M. EM at an angle of delta M. Okay? EM at an angle delta M. Can anybody tell what is the equation for this PE, electrical power? Just now we have written one equation like mod E into mod V by XS into sine delta. Na? Mod E into mod V by XS into sine delta. Now that electrical power flow equation, P is equals to magnitude of the voltages product mod EG into mod EM, mod EG into mod EM by what are the overall reactance of network between the two voltage sources? What are the reactance between the two voltage sources? Xg plus XL plus XM. Xg plus XL plus XM. Only reactance you have to consider here. It's not impedance. It's only reactance. Xg plus XL plus XM into sine of the angular difference between the two voltage sources. The angular difference between the two voltage sources will be delta G minus delta M. The angular difference between the two voltage sources is delta G minus delta M. Now I'll call this Xg plus XL plus XM as equivalent transfer reactance between the two voltage sources. Xg plus XL plus XM. I'll call this as X equivalent. So equivalent transfer reactance between voltage sources. Next one. The delta G minus delta M, delta G minus delta M, that you call as rotor angular difference, simply delta. I'll write in next slide. If you have completed, I'll move to next slide to write about that delta G minus delta M. So the delta G minus delta M we call as delta. This is rotor angular difference. Between the machines. Next. So in that way, that electrical power PE you can write as simply magnitude of the induced EMFs of two machines, EG into EM by equivalent reactance into sine delta. Equivalent transfer reactance into sine delta. Yeah. EG into EM by X equivalent into sine delta. That's the electrical power equation. So I'm making one small assumption now in this steady state stability analysis. The steady state stability analysis, we are making one small assumption. That is, this EG into EM by X equivalent is constant. You assuming EG into EM by X equivalent is constant. So it will look like PE equals to some constant into sine delta. Electrical power equals to some constant into sine delta. This constant is our assumption. Let Eg into Em by X equivalent is constant. So it is some constant into sine delta means the signal looks to be a sinusoidal signal. Right? Signal looks to be a sinusoidal signal. That I am going to plot, which we call generally power angle curve. Power versus rotor angle curve. Power angle curve. I'll show in the next slide that power angle curve. Yeah, please complete this one. So I'm showing X and Y axis here. This axis is for delta, X axis, and Y axis I'm showing power. Y axis I'm showing power. Power, and this is delta. So it's sinusoidal signal in the sense I'll show the signal like this. Okay, and this is the peak value of this signal, which is nothing but Eg into Em by X equivalent. Peak value of the signal is Eg into Em by X equivalent. At how much angle you are getting it? At how much angle you are reaching to the peak? 90 degrees. You are reaching to this peak at an angle of 90 degree like this. At 90 degree, we are reaching to the peak. Yeah, next. Next, listen here. Initial operating state, I want to tell you. Initial operating state. You assume this whole system is a lossless system here. Whole system, it's a lossless system. Means we don't have any mechanical losses as well as we don't have any real power loss in the connected network. In that particular way, in the initial operating state, mechanical input given to the generator, PS1 value, and electrical output of generator, PE1, these two are exactly equal. Mechanical input PS1, electrical output PE1 are exactly equal. And this electrical power, what it is flowing through line, and this PE2. So definitely this PE1 and PE2 also equal. Of course equals to PE. PE1, PE, PE2, all the three are equal. And we don't have any loss in the motor also. So electrical power input PE2, mechanical output PS2, these two things also equal. It's simply what I am saying from this network is in the initial state, mechanical input of generator, electrical power flow in the network, mechanical output of motor, all these three values will be equal. Okay, yeah. So I will say here, in initial state of operation, PS1 equal to PE1 equal to PE2 equal to PS2. Okay, PS1 equals to PE1 equal to PE2 equal to PS2. Not only that, the speeds of these two rotors. First, generator rotor speed is omega g, motor rotor speed is omega m. Generator rotor speed omega g, motor rotor speed is omega m. These two also exactly constant, equal. Omega g, omega m also equal. So generator rotor speed and motor rotor speed both are exactly equal. See, if these two are equal, if both rotors are rotating at the same speed, how is the angular difference between these two rotors? Constant. We will assume that angle is delta naught. That's the initial rotor angular difference, right? So that implies delta is constant. Delta value was constant at delta naught. Delta value was constant at delta naught. So I am showing that angle here in this graph, power angle curve graph. Delta naught angle I am showing in the power angle curve graph. This is that angle, delta naught. So with respect to the delta naught angle, whatever the electrical power you have, this is the power what it is flowing in the network. or initial electrical power flow, you can say, which is PE naught, which is PE naught. I have made that assumption and uncertainty. Why you are questioning that again? I said already, we assume that system is lossless and we have taken the PS1 equals to PE1. Yeah, look here, look here. This is the initial operating point A. This is our initial operating point as A point. So initial operating point is A. Operating point is A. Operating point is A. Yeah, next thing. Listen, I will show these two rotors also in the phasor diagram, something like this. Just observe. Here this is delta axis. Okay, tell me, which rotor is in leading among these two? Which rotor will be in leading among these two? Is it generator or motor? Which rotor axis will be in leading? Is it generator or motor? Generator. Generator, right? So generator rotor will be in leading with respect to motor rotor. So let's show. This is the generator rotor axis like this. It is the generator rotor axis I am showing. Rotor axis of generator. Next, I am showing rotor axis of motor here. Something like this. It is a rotor axis of motor. Rotor axis of motor. And the angular difference between these two is delta we are showing. And you know that this generator is rotating at a speed of omega g. And motor is rotating at a speed of omega m. Generator is rotating at a speed of omega g. Motor is rotating at a speed of omega m. Fine. Next. Till now we don't have any disturbance. We have discussed only basic things here. Next thing. Listen here. Suddenly, I made a small increment on the mechanical load of the motor. PS2 value was little increased. Listen to my question first. Whenever you make a small increment on the mechanical load of motor, what will happen to speed of motor? It won't change instantaneously. All of a sudden, it won't change. But because of the extra load what you have added, or extra weight what you have added, there may be a possibility to say that omega m value starts decreasing. Motor speed starts decreasing now. Is it clear? Right? So I am saying here, a small increment in mechanical load of synchronous motor was done. A small increment in mechanical load on motor shaft was done. Means PS2 value was little increased. Okay, next thing. Because of this little increment in the PS2, motor speed little decreases. And definitely you can expect that this motor will rotate at lower speed compared to generator speed. Omega m will come less than omega g, definitely. Omega m will come definitely less than omega g. See, whenever this omega m is becoming less compared to omega g, what is happening to that angle delta? Definitely increases. Yes or no? Tell me please. Definitely that angle delta is going to be increased, we can say. Fine. So delta is going to be increased. We can say. Well, because of the delta increment, delta value will become more than delta naught, definitely. So as and when this angle delta naught is increasing like this, what will happen to electrical power? Because of this increment, we are going to get some new electrical power, something like this. Because of that angle increment, definitely we are going to get some new electrical power. Okay, see that new electrical power means electrical power flow in the network was increased. That electrical power increment what we have here, electrical power increment what you have here, it is capable to meet the extra load what you have added. It is capable to meet the extra load what you have added. Then obviously we can say that as and when we are adding extra load, the system is capable to supply that extra power. Extra power in that particular situation, we can say that the system will be stable. But you see, whenever you are saying this PE is increasing, this PE increment should be met by PS1 increment only. This PE increment should be met by PS1 increment only by means of energy conservation. Yes or no? Whenever you are asking more energy output, obviously you should supply more energy, right? Obviously you should give more energy as input. So this PE2 is increasing. This PE2 increment is going to be met by increment in the PS1. But it will take some time. Within that time, this angle delta is going to make some oscillation, and finally it will stay at some point definitely. And then we can say that the system will be stable. Yeah. So all of you getting this one? What is it? Tell me. I will write the things what I said now. Look here. So delta is increasing. That implies electrical power input will increase. PE2 you write simply. PE or PE2 will increase. Right? This increment will meet the increment in PS2. Increment in PS2 means whatever the load you have increased, that change it is going to meet, I am saying. Right. And finally, at some time, the system will be stable. System will be stable. Yeah, you write in bracket. The increment in electrical power flow shall be met by the increment in steam input to alternator or to the generator. Definitely it has to be met by the increment in the steam input by generator. Fine. Definitely the present electrical power flow, what you are saying, it is higher than the previous electrical power flow, right? Present electrical power flow is higher than the previous electrical power flow. Because of that, definitely that new operating point may come as some point as B here. That new operating point will be shifted above, and your resultant angle will be definitely greater than delta naught. The resultant angle will be definitely greater than delta naught. Okay. Next, our new settling point is B here. Now, again, I will say in the similar way. Again, look here. All of you stop writing. Again, I make a small increment in PS2 value. After making that small addition of load to that shaft of the rotor, then definitely speed of motor will decrease. Whenever omega m value was decreasing because of the decrement, angle delta is going to be definitely increased. Because of that increment in the delta, definitely that electrical power flow in the network will increase. Right? Whenever that electrical power flow is increasing, that increased electrical power flow, what you said here, that is going to meet the requirement of PS2. That's going to meet the requirement of PS2. Of course, This PE2 increment, what you said there, that is met by PS1. That is met by PS1. That you should say internal. That you have to say on your own, obviously. Like that, what I am doing is continuously, not in one shot, continuously. I made a small increment in PS2. Look here. Made a small increment in PS2. Speed of motor was changed, and it has settled down to some value, and delta was increased and settled down to some value, and system reached to steady state. Again, after settling down, I made a small increment in PS2. After doing that, again, speed of rotor will decrease and delta will increase, and again electrical power flow will increase. Okay, again it made some oscillation and finally settled down to some point. Right, waited some time. Again we made a small increment in PS2. Like that, continuously with time gaps. I made small increments in PS2. Right? And I made small increment in PS2. Because of that, electrical power is increasing and the system is settling down to some angle. Like that. Finally, I met to this point as C. That I am going to write. Okay? Kindly observe. Like this. Small increments of PS2 are made. Right, with some time intervals. And system reaches to steady state at each point. And finally operating point reaches to C. Finally, operating point reaches to C. Yeah. Finally, operating point reaches to C. Next, at C, after standing at the point C, if I make a small increment in the mechanical load, PS2, what will happen? That we have to discuss. Okay? Yeah, let's move in the next slide. You please complete it quickly. Yes. See, at C point, well, angle is 90 degree. If you want to write in bracket, angle equals to 90 degree. If PS2 value was little increased, what will happen to omega m? Rotor speed, motor speed, what will happen? Decrease, definitely. Whenever you add extra load on the motor, irrespective of anything, definitely motor speed starts decreasing. That's it. Right? So motor speed will decrease. This is a very physical phenomena what you have to understand. Whenever motor speed is decreasing compared to generator speed, of course, this angular difference delta will increase. See, whenever the delta is increasing, obviously your electrical power flow on this graph will be shifted something like this. Because of this angle increment, electrical power flow will be shifting down like this. Means what you can expect is electrical power flow in the network starts decreasing. Okay, so because of this, from curve, electrical power flow is decreasing. Yeah, please kindly listen my words. Actually, we added some extra load on the shaft of the motor. By adding that extra load, what we will expect is this motor will draw some extra power from network. extra power from network, and it's going to satisfy the load. That's what the thing we have expected. But in a reverse way, what it's happening is, after adding some extra load on the motor, rather than drawing excess real power, excess electrical power, it is reducing its real power absorption. It is reducing its electrical power drawn. See, as and when it is decreasing that electrical power drawn and mechanical load is high, definitely the motor speed further decreases. I don't know whether you have understood this or not. Because of this, omega m further decreases. Because of more mechanical load and less electrical power input. Yeah, I am explaining again. Very simple topic only. This is a motor. Okay, this is an electrical power input. We have PE2, and we have some mechanical load as PS2. Whenever PS2 is increasing, our expectation is that PE2 will increase, but it's not happening. PE2 value was falling down. Electrical energy input is less, but mechanical energy demand is more. Electrical input is less, mechanical energy demand is more. What will happen? Rotor speed will decrease, right? Rotor speed will decrease. Why it will happen means, listen all of you. Why it will happen means simply, in between that input energy and output energy, we have some stored energy in the machine. Which is going to be called as kinetic energy of the machine. See, whenever you are demanding more energy output, but you are supplying less input energy. Output energy demand is more, input energy is less. But to meet that extra energy output what you have, the rotor will be losing its kinetic energy. And the kinetic energy is getting converted to the mechanical energy demand to satisfy the energy balance. So in that particular sense, definitely speed of the rotor starts decreasing, we can say. Okay, speed of the rotor is decreasing. Because of that omega further decrement, delta will increase further. If delta is increasing further, what is happening to the electrical power flow PE2? Just from this curve, you can see. If delta is increasing further, what is happening to that electrical power? Further falling down, right? Electrical power was further falling down. So that implies PE2 further decreases. Because of this decrement, omega m further decreases. And again, delta further increases continuously. Right? This is going to happen continuously. Delta further increases continuously. Yeah. Yeah. Yes. Why PE2 decrease physically or practically? Practically, Dinesh. Practically. Next. Delta increasing continuously and omega m continuously decreasing. So as the delta is continuing to increase, electrical power flow in the network is not constant with respect to time. If it is not constant with respect to time, the output is unbounded output, and we can say system will be unstable. So I think all of you clear at this point. Why omega m is decreasing? What is the reason? Pramod. Why omega m is decreasing? Because of load increment. Simple reason. Whenever you add some load extra on the motor shaft, definitely speed of the motor will decrease. That's it. Anywhere, either it is in the first case or second case, whatever it is, whenever you add some extra load on the motor shaft, speed starts decreasing. Yeah, next. Listen here. Just we will make some conclusion between these two. Kindly observe in this graph. Up to this point C means you can say up to 90 degree. As you are many of you are interested to discuss about 90 degree here. Okay. At this 90 degree. before that 90 degree, below that 90 degree angle, look Alaf. Whenever mechanical load is increasing, mechanical load PS2 is increasing, what is happening? Omega m decreasing. Omega m decreasing. Because of that omega m decrement, delta is increasing. Delta is increasing like this. Whenever the delta is increasing like this, what is happening to that electrical power value? Electrical power value also increasing. Electrical power value also increasing. That's the thing what you have to sense here, exactly speaking. Whenever below this 90 degree angle, whenever you are adding extra load, speed is decreasing, okay, delta is increasing, okay. Because of the delta increment, electrical power flow is increasing. That increment in the electrical power flow is going to meet the load requirement. Right. Beyond 90 degree, if you see, beyond 90 degree point, if there is an extra addition of load, listen to me, don't confuse. If there is an extra addition of load, PS2, load on the motor, if that is increased, speed is decreasing. Because of the speed decrement, delta is increasing. Delta is increasing like this. But as and when this delta is increasing, what is happening to this electrical power value? What is happening to that electrical power value? Decreasing, right? Because of increment in the angle, electrical power flow is going to be decreased. In this case, you are saying the system as unstable. Why? In the sense, the system what we have is unable to meet the load demand. Right? The system what we have is unable to meet the load demand. In that particular situation, we are going to say that the system will be unstable. Okay. Whereas in the first case, whatever the load change you make, that is going to be met by the system. So in this particular situation, we are going to say the system as stable. In the other case, we are going to say that the system as unstable. We are going to say that the system as unstable. Yeah. Fine. Now, with respect to delta variation and power, if you talk, delta PE by delta, here delta PE number is positive, delta is also positive. So delta PE by delta, if that is positive, we can say that the system is stable. Similarly, delta PE by delta, if that is negative, because delta PE is negative, delta is positive here. In that case, we are going to call the system as unstable. Okay, right. So I'll say the system is stable. The system is stable for just look here. Delta PE is positive for delta positive. Or you can call simply the ratio delta PE by delta is positive. Delta PE by delta is positive. See, we are discussing about very small disturbance, right? Very small disturbance means obviously delta variation will be very, very less. As if delta variation is very, very less, this delta PE by delta we can rewrite as dPE by d delta. For small variations in the angle, we can replace this delta PE by delta as dPE by d delta. If that is positive, or you can say greater than 0, or you can say this dPE by d delta is greater than 0, then we can say that the system is stable. Then we can say the system is stable. Yeah. Next thing. We'll talk about angles also. The system is unstable. System is unstable. For what condition? For what condition the system is unstable? Delta PE value is becoming negative for an increment in the angle. Means for a delta positive, delta P is becoming negative. In that case, we are saying that the system is unstable. Or you can call delta PE by delta delta. This number is negative. That implies dPE by d delta value is negative for small disturbance. Or you can call rate of change in real power with respect to angle is less than 0. Rate of change in the real power with respect to angle is less than 0. Yeah. Fine. See, what do you mean by dPE by d delta simply? What do you mean by the dPE by d delta here? From this graph, what you can say that? From this graph, what you can say that? That is nothing but rate of change in the real power with respect to angle. Nothing but slope. There's nothing but slope. Slope of the power angle curve. Means if the slope of the power angle curve is positive, we will say system is stable. If the slope of the power angle curve is negative, then the system will be unstable. This is one comment you can make. But strictly speaking, saying a term like slope of power angle curve positive, system is stable, slope of power angle curve negative, system is unstable, it may not make a clear sense. It may not make a clear sense. What you should say exactly is whatever the present operating point we have, if that is existing in the positive slope region, whatever the present operating point we have, if it is existing in the positive slope region, then we can say that the system will be stable. Okay, whatever the present operating point we have, if that is existing in the negative slope region, then we can say that the system will be unstable. These comments you should make. Okay, right. So I'm saying here, if operating point lies in dPE by d delta greater than 0 region, positive slope region, okay, greater than 0 region, then system is stable. In opposite, if operating point lies in dPE by d delta, means negative slope region of the power angle curve, then the system is unstable. For what angle you have the positive slope here? For what angle you have the positive slope? Tell me please. For what angle you have the positive slope? Just look at the power angle curve. Delta less than 90 degree, we have the positive slope. Delta greater than 90, we have the negative slope here. Okay. So if you want to write here itself, delta greater than 0 will happen for an angle delta less than 90 degrees. And this negative slope will happen for an angle delta greater than 90 degrees. For example, if dP by d delta is equals to 0, means operating point where you are standing, at that point dP by d delta equals 0. What we should say? Definitely that point where you are standing, particularly here, this is a point C. At this point, definitely I can say that we are at the margin of the stable region, margin of the unstable region. We are staying at the margin of the stable and unstable region. So at this point, we can say the system is marginally stable or marginally unstable. We have different statements to that. Critically stable, critically unstable. Okay, yeah. So let me write that comment also quickly. If system operating point, better. If operating point is at 0 slope location, dPE by d delta equals to 0 point, then system is either marginally stable or marginally unstable. marginally stable or marginally unstable. Either it is marginally stable or marginally unstable. And at this point, angle is, at this point, the angle is 90 degrees. At this point, the angle is 90 degrees. We are going to call the delta equals to 90 degree as stability angle. Delta equals to 90 degree, we are going to call as stability angle. Stability angle. Right? Stability angle. So that's the angle below which we say system is stable, above which the system is unstable. But if anybody asks you, maybe in the examination, as well as in some interview, if anybody asks you, when we say the system is stable with respect to angles, under steady state, we are discussing this one only under steady state operations, so-called for small disturbances. If somebody asks you, what you should answer is not with respect to angles. You should not say delta less than 90 degrees system is stable, delta greater than 90 degree system is unstable. That's not the thing exactly what you should say. What you should say is with respect to slope always. Whatever the present operating point you have, if that lies in the positive slope region, then the system is stable. If the present operating point lies in the negative slope region, then we have to say the system as unstable. These only the comments what you have to make. Later on, if they ask about what is that angle and all, you should say, if the network is consisting only reactance, if the network is consisting only reactance like this, then you get a power angle curve in this manner, where we have a positive slope region for an angle delta less than 90 degree, and we have the negative slope region for an angle delta more than 90 degree. That comment you should make. Actually, this 90 degree point, what you have, delta less than 90 stable, delta greater than 90 degree unstable, that is decided by your network nature. Decided by the network nature. But all the time, irrespective of that network nature, is it in reactive nature or resistive in nature or capacitive in nature? Doesn't matter. Whatever it is, all the time, what you should say is, if the operating point lies in the positive slope region, it is stable. If it lies in the negative slope region, unstable. That statement is a valid one universally, irrespective of the network type. But practically speaking, the interconnecting network may be in reactive nature. That's why the people might be using in a what we call in a concluded way, delta less than 90 stable, delta greater than 90 unstable. Okay, yeah. So I think all of you getting this one, what I have discussed. Yeah. So I have a break for 15 minutes. After break, I'll try to extend the same study. And I will be discussing why we are going to do stability analysis only for synchronous machine. Why we are not doing this stability analysis for the what we call induction motor, right? That we are going to discuss. Right? So 15 minutes break. So I have resumed audio video on screen. Right. Look here. So I'm taking up in the next slide. Next slide. All of you just listen to this. Just stop writing. Stop writing. Just listen to this. Just listen to this. This is generator with some reactance, and we have a line. Line like this, having some reactance for line, and this is motor like this way. Just look here. So this is some mechanical input. We are saying PS1, and this is some electrical power flow in the network as PE, and we have some mechanical load on the shaft as PS2. Mechanical input PS1, mechanical output PS2. We have the electrical power flow in the network as PE. We have some term here that is EG into EM by X equivalent, so-called peak of this curve. Peak of this power angle curve, EG into EM by X equivalent. Okay. That value we will call as P maximum right now. I will tell the definition after little time. After a little time, I will try to tell the definition. EG into EM by X equivalent, we are naming that as P max. P max. Okay. Next one. Listen all of you. Maximum power transfer capability of this network, what we have given here. Maximum power transfer capability of the network, what we have shown here, that is, let us say some number 600 megawatts. 600 megawatt, that is a maximum power transfer capacity of the network. 600 megawatt. All of you, Adarsh, kindly look here what I am saying. Adarsh. Right now, at the present operating condition, PS1 value 200 megawatt number, electrical power flow 200 megawatt, mechanical load 200 megawatt. All the three are exactly equal. That's the initial state of operation. 200 megawatt mechanical input, 200 megawatt electrical power flowing, 200 megawatt is a load, mechanical load on the shaft of the motor. According to the study, what we have done till now, 200 megawatt point means in the power angle curve I will show you. In the power angle curve I will show you that 200 megawatt point. Just look. So these are the axis of power and delta. Okay, the power axis, and this was delta axis. Power angle curve I am showing like this, and this peak of this curve is how much number? What's the peak of this curve given? 600, right? This peak value was 600 megawatt. 600 megawatt is a peak value. Next, what is the present power flow in the network? 200. I am showing the 200 here. This is 200 someplace. Megawatt. With respect to that, this is your initial operating point on this side. Initially, the system is stable. Means obviously your operating point will lie in the positive slope region of curve only, right? See, for the 200 megawatt, there is some other point on this side also. But that point is lying in the unstable region. But we are saying that initially the system is stable. So this is your operating point, what we have to consider. Okay, next. Suddenly, I made a small increment for this mechanical load. Means power value was increased to 205 megawatts. I've increased the mechanical load on the shaft of the motor to a number 205 megawatts. Anonymous attendee, kindly listen here. whenever you are increasing that mechanical load, whenever you are increasing mechanical load, or whenever you add some load on the shaft of the motor, definitely mechanical energy output will be more compared to electrical energy input. If mechanical energy output is more compared to electrical energy input, the excess mechanical energy demand should be met by the rotor only. Means rotor should lose its kinetic energy and it has to feed to that mechanical demand what you have made. By that way, rotor speed starts decreasing. Else, it's a general physical phenomena. General physical phenomena. If you have a running motor, if you add some extra load on that, definitely speed of that is going to be decreased. Fine. Now, listen here, listen. Because of this, as we said now, speed is decreasing little bit and delta is increasing little bit. So because of the delta increment in this manner, because of the delta increment, definitely electrical power will increase. And finally at some point, this power will be changed to 205 megawatt. This power will be changed to 205 megawatt. And this excess electrical power, what you have, listen all of you. Excess electrical power, what you have here, that is going to be met by increment in the PS1. That is going to be met by increment in the PS1. Following all of you. So all the three powers are equal now. 205, 205, 205, all the three are equal and system is in the stable mode. And again, I made this power to a number 210 megawatt. 210 megawatt. Again, electrical power flow also increased to 210 megawatt. And this value also I increased to 210 megawatt by means of the mechanical input to the generator. Like that, continuously, I made a small increments in the mechanical power demand. And finally, I have reached to a power of 600 megawatt. Finally, I reached to a power of 600 megawatt, which is a P maximum value. Electrical power flow value also reached to 600 megawatt. Mechanical input also I made it 600 megawatt. This is completely within my hand. PS1 is completely within my hand. I have increased that value according to the electrical power variation continuously, and I reached to 600 megawatt. All the three values are exactly equal. All the three values are exactly equal. Now, this is that operating point which we are touching. This is the operating point which we are touching. Now, listen all of you. Listen carefully. Beyond this point, if you made a small increment in mechanical demand, PS2 value, I made as 605 megawatt, let's say. I've increased the mechanical demand to a number 605 megawatt. Because of that, again, speed of the motor is decreasing, angle is increasing. Speed of the motor is decreasing, angle is increasing. Because of that angle increment, observe here, because of that angle increment, electrical power flow is decreasing below the value of 600. Electrical power is decreasing below the value of 600. Maybe this power, I am saying, it is becoming, let us say, 590 megawatts. That's decreasing below 600 megawatt and it's becoming 590 megawatt. Right. Is it the decrement you are making because of PS1? Is it the decrement in the real power because of this PS1? Tell me, anybody. Please tell me. Yeah. Is it the decrement in the electrical power coming because of the PS1? No, it's not due to that. It's not due to that. See, whatever the 600 megawatt you are saying now, 600 megawatt, who is offering this limit? Who is offering this maximum power transfer limit? Is it your generator or network? Who is offering this 600 megawatt power limit? Is it your generator or network? Network. It is offered by the network. So that's why we can say this P maximum value what we have here. P maximum value what we have here, it is going to be called as steady state power transfer limit of the network. Steady state power transfer limit of the network. In the sense, the network between the two voltage sources. Network between the two voltage sources is unable to transfer the power beyond 600 megawatt. beyond 600 megawatt. All of you getting this one? Please tell me. Yeah. So I can say this P maximum is going to be called as maximum power transfer capacity of the network. Maximum power transfer capacity of network. Or steady state power limit of the network. The meaning of that is very simple. It is a power limit. Beyond which the system will lose the synchronism. If you attempt to transfer the power beyond this value, the system will be losing the synchronism, right? It is the power limit beyond which the system will lose synchronism. System loses synchronism. Loses the synchronism. Okay. Yeah. Next thing. Listen, I will try to explain similar thing in different way also. Aishwarya, just listen here what I am saying you. In the second way, what I am saying here, it might clear what's the doubt you have, right? Yeah. Listen here. So same, I have one generator like this with some internal reactance, and this is one transmission line, and this is a synchronous motor we have. And again, I am saying maximum power transfer capacity of network is 600 megawatts. Okay, so this is mechanical input PS1, electrical power flow is PE, and this is PS2. The demand is PS2. Yeah, look all of you what I'm saying. Look this. See, we create a type of situation here to understand this one. We assume that initially this PS2 value was 200 megawatt, and this PS1 is also 200. So obviously this network should transfer a power of 200. Megawatts. Okay. Now we created a situation that whenever I increase the load demand on the motor side, immediately I will give some information to the generator. That I have increased my load by this much amount. Please increase your input. Means please increase what we call mechanical input to your generator. That is the information what I am passing here. In that way, you assume it. Getting me? I'm repeating the terms. Very simple. We are going to increase the PS2. Whenever I make that increment, irrespective of network and all, whenever I make this increment, just I am informing that increment to the generator, right? Saying that you have to increase your mechanical input by this much amount because I have increased my load. So in that way, I made this value from 200 to 205. Immediately, I informed to the generator that I have increased the power demand by 5 megawatt. Please increase your mechanical input by 5 megawatt. It is accepted, and it is increasing to 205. And what will happen to electrical power flow in the network? Anybody please tell me. After doing this one, what will happen to electrical power flow in the network? It becomes automatically 205, right? Because input is 205, output is 205. Nobody is responding. What happened? It will be obviously 205. Okay, done. 205 megawatts. Next thing. Again, PS2 value I am increasing to 210 megawatt. I inform to the generator that I increased the power demand again by 5 megawatt, please increase your mechanical input by 5 megawatt. So it has increased this value to 210 megawatt. Then what will happen to electrical power flow? Also 210 megawatt. Also 210 megawatt. Like that continuously, I made this increment up to 600. Up to 600. And I informed to the generator that my power demand is 600. Please make your mechanical input also 600. So by stepwise, it has reached to 600. And how much is power flow in the network? Again 600 megawatt. Power flow in the network will be again 600 megawatts. Okay, next one. Now beyond the 600, this motor is saying that I am increasing my mechanical requirement, mechanical load to a number of 605. To a number of 605. Please increase your mechanical input to 605. Whether this generator will increase its input to 605 or not. Whether this generator will increase its input to 605 or not. Yes, definitely. Why no, Pranjali? Why Meena, no? Why? Why it will be no? That mechanical input is completely in your control, right? This mechanical load is completely in your control. Whenever I am increasing this mechanical load, simply I am saying to the generator that you increase your mechanical input by the same amount what I am making. So this generator also accepted. To a number of 605 megawatt. But PE decreases. PE will not become 605. It may be 590 megawatt. That's the issue what we are facing. Following all of you. So the network is having some limit. Beyond which it can't transfer the power. But mechanical input, you can make any number according to your wish. Mechanical load, any number according to your wish. But the connected network is not accepting to transfer a power beyond 600 megawatt. This is what we are saying as stability limit, or you can say power limit. So I think all of you clear, I think. Anonymous attendee, why you are saying this question to me? Pmax of the network, I am saying you already. This PS1 is completely within your control. You have abundant steam energy. We are capable to increase the mechanical input. What's the doubt in that again? Again, why you are saying me to stick to 600? 600 is the power limit of the network, not the generator, not the mechanical input of generator, not the mechanical load of motor. Yeah, fine. Now, why this electrical power is decreasing? Beyond this point. Yeah, correct. Beyond this point, this electrical power is falling down. Beyond the increment in the delta, more than 90 degree or more than this point, electrical power is falling down. That is making this system as unstable. See, you observe now. We have some mechanical input to the generator. Just listen to me words. We have some mechanical input to the generator, but electrical power output is lower than this number. In this case, you observe. In this case, please you observe in this case. We have some mechanical input, but electrical power is decreasing continuously. In case of generator, I am talking. In case of generator, we have some mechanical input, but electrical power output is continuously decreasing. Then where the input energy is going? Output energy continuously decreasing. But you have some input energy. Where that input energy has gone? That has stored into the rotor of this generator. So I can say that kinetic energy stored in the generator is going to be increased. Means generator speed starts increasing beyond this point. But here, input energy is less. Electrical input is less. Mechanical load is more. Because of the excess output energy, the motor speed starts decreasing, we can say. Motor speed starts decreasing. And as time progresses, this electrical power is continuously falling down. continuously falling down, and this omega m, speed of the motor, continues to decrease, and speed of the generator continue to increase. Okay, so when we can say the system is unstable in this perspective is, if you have a synchronous motor in your stability analysis, if the speed of the motor continuously decreasing because of system will be unstable. If the generator speed continuously increasing because of the disturbance what you have made, system will be unstable. Okay, this is one simple comment we can make in the view of the stability. Yeah, so let's write that statement also here. The generator is unstable. Generator is unstable if its rotor speed continuously increasing during disturbance. Continuously increasing during disturbance. Or else you write simply as this generator speed tends to infinite, we can say system is unstable. System is unstable. Strictly it's a theoretical statement. Practically speaking, we don't touch to infinite value at all. Okay. Practically speaking, we don't touch to infinite because we have some what we call control mechanism, steam control mechanism and all. It may shut down the machine. It may shut down the machine if the speed is crossing certain limit. But theoretically, we can say if speed of the generator is tends to infinite, we can say the system is unstable. Yes, other statement we are seeing with respect to motor. The synchronous motor is unstable. Motor is unstable if its rotor speed continuously decreasing during disturbance. So means I can say as omega m value tends to 0, we can say system will be unstable. System is unstable. This may happen. As omega m tends to 0, we can say system is unstable. Okay, fine. Next. So next point, what I want to discuss here is, for example, in place of synchronous motor, if you have induction motor, what will happen? If you have induction motor, what will happen? In place of synchronous motor, if you have an induction motor, what will happen? That we want to discuss now. Yeah. So let's move in the next slide. I'll tell you. Very simple thing only. Don't complicate. Disturbance like load change or whatever the disturbance, whatever the load change you are making, that itself is a disturbance. Look, for example, so this is one synchronous generator. We have some reactance for this machine connected to transmission line, and this is some induction motor load. Okay. So this is that mechanical input PS1. Yes. This is some generator reactance and line reactance. What is maximum power transfer capacity of this network? Do you have any term like maximum power transfer capacity of this network? Maximum power transfer capacity of network. See, actually, listen here. Actually, this induction motor, what we have, it does not have any voltage source, right? This induction motor does not have any voltage source. If we don't have any voltage source, we don't have two sources in the system at all. We don't have two sources. Only one source is existing. Means we have only one induced EMF in the system. We have only one induced EMF in the system. We don't have the second induced EMF. We don't have the second induced EMF, so that we don't have a concept of maximum power transfer limit of the network in this condition. We don't have a concept of maximum power transfer limit in this particular condition. Yeah. So some of you might have a doubt here. Might have a doubt. In fact, even before moving to this induction motor, I'll try to tell about the synchronous motor only again. Synchronous motor. Just let's take one more slide. Just look here. Look here. Okay. This is one generator, and we have a line here. And this is connected to one synchronous motor. What we are saying. Many times. Very, very simple questions I will ask you. Very, very simple questions. We have some induced EMF in this generator, EG. Only magnitude I have written. We have some induced EMF in the stator of this motor as EM. We have an induced EMF in the generator stator, EG. We have an induced EMF in the stator of the motor as EM. This is having a frequency of FG. This is having a frequency of FM. This is having a frequency of FG. This is having a frequency of FM. Anybody tell me please, who will decide? Frequency of this generator. Frequency of the induced EMF in the generator. Who will decide it? Generally, speed of the rotor of generator will decide it. Yes or no? So it is decided by omega g. Whatever the generator rotor speed you have, that will decide this frequency. And who will decide this frequency? Yeah, I am asking very simple question. This FM value, what we said, frequency of this induced EMF in the motor stator, is it depends upon the frequency of this bus bar? I don't know whether you have understood this or not. Look here. Look to the statement kindly. Whatever the frequency of induced EMF in the motor state we have FM, whether this frequency value depends upon the bus bar voltage frequency or not. Depends on the bus bar voltage frequency or not. No, it won't be depending. It will be depending on its own rotor speed, right? It will be depending on its own rotor speed, yes or no? Getting me? Please be clear at this point. So this FM depends or decided by the rotor speed of the synchronous motor. Following all of you? Yes. Good. Now the question is whether this FG and FM values are equal or unequal. Whether this FG and FM are equal or unequal. But if we have to connect to machine to bus bar, just look here what I am saying you. Huh? Why you are doing cross questions? Just look here. How are these frequencies? Whether these are equal or unequal? May or may not be. See, if these two frequencies are equal, listen please. If these two frequencies are equal, I will say that both machines are synchronized. I'll say that both machines are synchronized and we have a proper exchange in the real power from one machine to the other machine. If these two frequencies are becoming unequal, I can say these two machines are not synchronized properly. If the machines are not synchronized properly, we don't have a proper exchange of the real power. Yeah, is it okay now? Yeah, whether the machine is a lossless one or not a lossless machine, FG equals to FM. That's it. Vaishnavi, why you are calling that lossless here? Yeah. So I will write this one. I will write this one. Kindly observe. If Fg is equals to Fm, then Fg is equals to Fm, then both machines are synchronized together. Both machines are synchronized together. Synchronized together. And if these two frequencies are unequal, Fg, Fm, these two are unequal, then there may not be proper real power exchange. There may not be a proper real power exchange. Proper real power exchange. And system may be unstable. System may be unstable. May be unstable. I'm talking this only in the steady state operation, not in the transient time. Not in the transient time. Synchronization is definitely decided by the frequency. Delta will not become 0. If the machines are properly synchronized, delta will not be 0. See, listen again. Whenever you create some disturbance here in the system, there is a change. Listen, please. Listen, all of you. Whenever you have a disturbance in the system, there is a change in the generator speed as well as there is a change in the motor speed. Because of change in the generator speed and motor speed, there is a possibility of change in the Fg value and Fm value. Because of the change in the induced EMF frequencies, we have a single system operating with two frequencies here. Single system operating with two frequencies, then there may not be a proper real power exchange in the transient duration. Even after reaching to the steady state or after long amount of time, still, if you are feeling some differences are there between Fg and Fm, we will say that the system will be unstable. Right? So, for example, disturbance occurred. There is a small difference in the frequencies. Small difference in the frequencies of the machines. Okay. After some time, both machines' frequency got equal. After some time, both machines' frequency got equal. I would say definitely the system will be stable after reaching the steady state. Is it clear? Yeah. Now you tell me, in this particular case, very, very simple question. This induced EMF EG will have some frequency of Fg. This induced EMF will have a frequency of Fg. Who will decide this frequency? Decided by the rotor speed of the generator. Decided by rotor speed of generator. Rotor speed of generator. Do you have any second frequency here? Do we have any induced EMF in the induction motor stator? Tell me all of you. Do you have any induced EMF in the induction motor? No. We don't have any induced EMF. So there is no second frequency in the system, right? There is no second frequency in the system. Whatever the system we have, it will operate at this frequency only. Do you have any problem of the system stability in this case? Do you have any problem of the system stability in this case? Yes or no? No. See, actually, we don't have a problem of the rotor angular stability here. We don't have a problem of the rotor angular stability. No problem of rotor angular stability. Rotor angular stability. There is no maximum power transfer limit of the network. No issue with maximum power transfer capacity of the network. Maximum power transfer capacity of the network. Yeah. No issue with the maximum power transfer capacity of the network. And whatever the rotor we have, that rotor speed will be decided by this input frequency only. And obviously we can say we have some slip and all, because of that the rotor speed may not be equals to synchronous speed and so on. No issue with the P maximum here. But whenever you increase this load on the induction motor continuously, whenever we are increasing the load on the induction motor continuously, generator is capable to supply by increasing its PS1 you assume, right? But because of this excessive load increment on the induction motor, current flow in the system will increase now. Because of that, this terminal voltage of induction motor may fall down. Terminal voltage of the induction motor may fall down. So there is an issue of voltage stability in case of the induction motors in the system, right? So, but there is an issue with voltage stability of the system. Issue with voltage stability of the system. Voltage stability of the system because of falling in the operating voltage. Because of fall in the operating voltage. So in this case also, will the network will carry 600? That depends upon your load now. That depends upon your load. Means if this load is demanding more than 600, the generator can supply. Because you don't have P max at all. You don't have that P maximum at all. You don't have the network limit in this case. Okay, now tell me, when the angular stability issue will come in the system? When the angular stability issue will come in the system? All of you, I need your response. Please kindly respond. When we will have an issue with the rotor angular stability of the system? If the system is consisting at least two synchronous machines. If the system is consisting at least two synchronous machines, then there is a problem of the what we call synchronism, or you can say the angular stability issue, right? So if you are not having two synchronous machines, for example, if you have only one synchronous machine and the other one is an induction motor or induction machine, then you don't experience any problem with the rotor angular stability. See, one more thing I said earlier, rotor angular difference. Rotor angular difference means it's an angular difference between two induced EMFs, right? It's an angular difference between two induced EMFs in the status of the machine. In case of induction motor, as you don't have that type of EMF, there is no meaning to say rotor angular difference. Following all of you, right? So I can say in the next slide as a conclusion, the problem of rotor angular stability occurs if the system consists at least two synchronous machines. At least two synchronous machines. At least two synchronous machines. Yeah. So some similar terms I want to tell you with respect to stability and all. Just have a look here. In the earlier statements we have written, no, dP by d delta greater than 0, system is stable, and it is less than 0, unstable, right? These statements we said. So if dP by d delta is greater than 0, we said the system is stable. Else we can say machines are in synchronism. In this case, we can say machines are in synchronism. Or machines are coupled together. Means rotating magnetic fields, or rotors also you can say. Rotors or rotating magnetic fields are coupled together. Whereas in case of unstable, I'll say machines lost their synchronism. Lost their synchronism means frequencies are not equal and gap is very high. Okay. Machines lost their synchronism. Lost their synchronism. Are not coupled together. Not coupled together. Coupled together. Or you can say out of step. Machines are out of step. Out of step. And in the earlier case, you can say machines are in step. Machines are in step. The case of system stable, you can say machines are in step. But there will be a limit for current. Yes, definitely. Definitely. Because of the current only, you are getting that limit of the voltage. Because of high rise in the current only, there is a fall in the voltage, right? But sir, practically we use induction motors as load in maximum cases. Yes, correct. We are using induction motors only in maximum cases, but you have number of synchronous generators. See, the stability problem will not come if you have only one synchronous generator, other one is a motor. If you have number of synchronous generators connected between network with various locations, definitely each and every generator will try to develop the induced EMF according to its rotor speed. Each and every synchronous generator will try to develop the frequency or will try to develop the induced EMF frequency at its own rotor speed. If the rotor speeds of machines are unequal, obviously frequency of induced EMFs are unequal. Obviously, you feel we have number of voltage sources with different frequencies. That may lead to improper real power exchange in the system. That is causing for out of step in the machines. Yes. Back EMF in induction motor. What is it? That's what I explained till now. Anonymous attendee, why you are asking the same question again? So these statements valid only for synchronous motor load, right? I explained just now. Right? Even though you don't have a synchronous motor, if you have number of what we call synchronous generators, definitely there is an issue of system stability. Sir, can you use a word synchronism in case of induction motor? No, we should not use a word as synchronism in case of induction motor. But we rotate the synchronous generator with the same speed. Yeah, if it is possible, Sai Charan, I will accept that we don't need to study the system stability. But it is not possible to rotate the synchronous generator always at the same speed. It's not possible. It's not possible to rotate the synchronous motor, right? So synchronous generator always at a constant speed. Okay, we will stop the session at this point and we'll discuss about some more things in tomorrow class, like the round rotor alternator, P maximum value setup, and then salient pole machine. Just those concepts I will discuss. After that, we take an alternator connected to a transmission line and then infinite bus bar. Till now, we said generator directly connected to infinite bus. Generator directly connected to infinite bus. We have discussed it till now. Later on, we will move on to that. Okay. Fine. Yeah, I think this announcement might have made by our institute people also. Offline classes will start from July 5th. Offline classes will start from July 5th. I think they have sent some mails to you also. Okay, you please inquire. You are asking about different centers, right? You ask the concerned people. And confirm it. You ask the concerned people, your branch managers, and you please confirm it. Yeah, for the people whoever is listening this class, if you have enrolled offline or online plus offline, for those people, your offline classes will start from July 5th. If you are from exclusively online batch, online classes might be continued to you again. Yeah, I don't know about that Gopal Krishna Reddy. Whatever the institute asked me to say, that I have said. That's it. For those who enrolled for online, only online. Yes. Online class will continue. May not be anything. May not be anything. Will take some more time. Yeah. If you have any doubt, you can raise your hands. If you have any doubt, you can please raise your hands. Tanvi. Tanvi, do you have any doubt, Tanvi?
Yes, sir. I have a small doubt in that induction machine, sir. You told
Tell me.
that. Yes, sir. Can you hear me, sir? Hello?
Tell me, please, Tanvi.
Yes, here it was said that the voltage magnitude falls down, sir. I forgot to note the reason. Could you repeat?
Simply, whenever you are adding extra load on the induction motor,
Okay, sir. Yes.
the speed of this induction motor will decrease. Why?
Okay, sir.
But
Yes.
current drawn by the induction motor is increasing, right?
Okay, okay.
Because of voltage drop in the network is more, voltage may fall down.
Okay, sir. Okay.
That may be leading to voltage stability issue.
That's it.
Okay. Any other doubt you have, Tanvi?
No, sir. Only one.
Yeah. Bharat.
Sir, where do we use a synchronous motor, sir? Can you give some practical examples?
What is it?
Where do we use the synchronous motors? The practical examples.
Synchronous motors. The people will use in some industry as a synchronous phase modifier to correct the power factor.
So these motors are used only in industrial level, sir.
Which
No,
one?
sir.
Synchronous.
Synchronous motors,
Yes.
not in home
We have
appliances.
this permanent magnet, sorry, BLDC motors, right?
Sir, DLDC.
BLDC motors, brushless DC motors.
Okay.
Those are equivalent to permanent magnet synchronous motors. Those are equivalent to permanent magnet synchronous motors, and those machines right now the people are using to manufacture the domestic fans, ceiling fans.
Okay. Sir, this power maximum limit is there, no? So that comes only when a generator is transferring power to synchronous motors.
It may not be. It may not be. May not be. See, for example, listen here. Whoever has any doubt here, just look. See, this is one synchronous generator I have considered.
Okay.
And this is connected to one transmission line wire like this. And this is a big power system network, whatever. Big power system network we have. See, we are connecting this generator to transfer some power to this big network.
Yes,
Bharat.
Yes, sir.
Okay. Tell me now, in the view of this operation, can I say this big network is acting as motor?
Yeah.
Understanding, Bharat?
Yes, sir.
Will it act as motor?
A big network means infinite bus.
You treat infinite bus or some generators, motors, loads, combination, whatever it is.
Okay.
Will it act as motor or not? Equivalent.
Yeah.
Why? Because it is drawing
Because
real
it's
power.
load. Yeah.
It is drawing real power, but there is a voltage source.
Okay.
Then it's the equivalent of motor only, right?
Yes, sir.
Then that's the combination of synchronous generator connected to synchronous motor.
Okay, sir. Then that's what I'm asking. So when a generator is
We may not have physical motors. We may not have the physical synchronous motors, but if I say simply one generator is supplying power to some network, I feel that the whole network equivalent is a synchronous motor to me.
there will be induction.
Inside this network, we have number of voltage sources having their own frequencies, right?
Yes.
Even though you disconnect it, but still this bus voltage will not fall down. This bus frequency will have some number. Understanding, Bharat, what I am saying?
Because there are another generators too in that.
Generators are there. Those are developing voltage and having some frequency. Definitely, this bus bar will have some own frequency, even though you connect this generator or disconnect the generator.
Okay.
Okay, in that perspective, this will be acting as synchronous motor only. Equivalent. Tell me, Bharat, any doubt you have more? Or still you have a doubt in this?
I didn't get that thoroughly, but I'll go through it, sir.
Yeah, please go through it and ask me again. Okay.
Okay, sir. So, and then one more doubt is you told about that frequency difference will be there when frequency mismatch. So that range is only plus or minus 2 or 3 hertz, no, sir? The range, the mismatch.
That you are saying in the steady state, 0.5 hertz in the steady state.
Yeah, in case of steady state only.
And the steady state, but in transient time, it's need not to be 0.5 hertz. It may be greater number also, right?
But in steady state, the range is what's the
Plus or
range?
minus 0.5 hertz.
Okay.
That's true. Yes.
Thank you, sir.
Yeah.
That's it.
Sai Charan.
Hello, sir.
Tell me, Sai Charan.
Sir, I made a conclusion with infinite bus bar. Can you correct it, sir?
Tell me.
Sir, infinite bus bar means as we have many connections like long connections which have many generators. Connecting this small unit of generator will not affect that much on the voltage
Big
and ratings of that bus bar.
Not rating, you say voltage and frequency. That's it. Don't say rating. Don't say rating.
Okay, sir. Sir, but for a big network, how can we assume that it has a constant voltage or a frequency, sir?
Constant voltage or frequency. Because if you reduce that into a single equivalent model, voltage source in series with reactance.
Yes, sir. That I understood, sir. Why we are equivalenting that to an ideal voltage of that only I'm asking, sir.
See, whenever you want to do analysis on this particular generator,
Okay, sir.
for example, this generator you want to analyze.
Yes, sir.
And I can't take up this whole power system network into the analysis to analyze the single generator, right?
Yes, sir.
So this power system network, whatever you have, that I'm converting into its equivalent.
Yes, sir.
Then we are doing analysis on the generator, what you want to do.
Okay, sir. So if we connect this small unit of generator and we supply PE to the Indian power system network, so some part of it is only changing, but if you consider whole of that Indian power system network, it is constant, no, sir?
Constant. Yes.
Okay, sir. Sir, starting today's starting like 10 minutes I got a network connection, sir. Network connection problem.
Yeah. What's the doubt you have in this?
Sir, in starting, sir.
This one only.
Sir, just you show me
This one
that
only, the starting slide of
okay.
today.
Dynamic system. Sir, 2F, sir, 2 and
Second
2.
one only I have opened. Sai Charan.
3 and 4, sir. 3, 4.
Okay.
Sir, in 3 last case, sir. 3F.
What is that?
Sir, in 3F last case, sir. Last
3F
graph.
last case. It is simply uneven waveform, uneven output you are getting.
Okay, sir. But what is the difference between third case and fifth case, sir?
You are unable to define that output value at a given time for both cases.
Okay, sir. Okay, sir.
Okay, then it will be an unbounded output, right?
Yes, sir. Sir, when we are comparing induction motor, before that we took a case, sir, for induction for synchronous motor and generator set.
Yeah.
Then in that you told we are doing in steady state, not transient.
Because we are making only small changes in the power.
Okay, sir. So after making small changes, when it is corrected and becomes steady state, we are analyzing in that steady state, sir.
In the statistic, yes.
Okay, sir. Okay. Okay, sir. Thank you, sir.
Yeah. Sarath,
Sir, good evening, sir.
tell me, Sarath.
Sir, I have a doubt like you said, no, sir, in while comparing both generator and synchronous motor,
Okay.
there you said, no, sir, rotor angle difference, delta. Said that the rotor angle is difference between both voltages. No, sir.
Angular difference between two induced EMFs.
But-
Else you can say rotor angular difference. Both will be same, right?
But why it was called rotor angle? Sir? Rotor angle difference.
That's what I have shown in this phasor diagram, right? That's what I have shown in this phasor diagram.
Yes, sir. But you said no, sir. The rotor angular difference is stator EMF's difference.
See, first machine is having some stator induced EMF. Second machine is also having some stator induced EMF.
Okay.
Angular difference between these two induced EMFs is delta.
Okay.
That's what I said. Angular difference between two Q axes, Q1, Q2.
Okay. Sir.
That is nothing but axis D1, D2 difference also, right?
Oh, okay, sir. Okay.
Getting?
I got it. Sir.
Yeah.
Sir, another doubt. You said no for induction motor there is no limit for power.
There is no power limit of network if you have an induction motor.
Okay, sir. But there is
because you don't have any induced EMF there.
Yes, sir. But
There is no definition for delta. Delta is angular difference between two induced EMFs.
Yes, sir. I got that one, sir. But for generator, there is some rating, no, sir. Up to that point only.
That and all okay. That and all we are not discussing right now. Generator will have having some rating beyond which it can't supply the power. That and all okay. If you are taking that limit also into the analysis, but you may fall in some difficulty of understanding P maximum.
Okay, because
that's why I have not taken up that rating of generator in this study.
Okay, sir. Because it is infinite bus, the power can be
in infinite bus in the sense whichever the amount of power you inject, it will take.
Yes, okay, sir. Okay.
Whichever the amount of power you supply, it will supply.
Okay, sir.
That is one property of infinite bus. Okay.
Okay, sir. Okay, got it, sir. Thank you.
Yeah. Kumar.
Hello, sir.
Tell me, Kumar.
Sir, here you said that mechanical power, sir, in like synchronous mechanical power increased behind 600, 605. Then generator mechanical power increased to 605. You said in that order explained.
Yeah.
I understand it, but can you explain in for step by step, sir? Like if fault occurs, first voltage drops and then current increases like that.
Same thing what you said. Whenever you are increasing mechanical load on the shaft of the motor,
yes, sir.
I am informing to the generator that you have to increase your mechanical input.
For understanding it, I understand, but there is nothing like that. Information like that, sir. What happens like in that case?
That's what I explained here, right? Without that thing, that's what I explained first. The first one.
Yes. Okay.
The first one, if you are increasing the power demand from 200 to 205, speed of the rotor is falling down because of the delta is increasing.
Yes, sir.
Because of delta increment only, this electrical power is increased to 205.
అదంతా అర్థమైంది సార్. సో ఇక్కడ 600 నుంచి 605 కి పవర్ ఇంక్రీజ్ అవడం వల్ల సో మనకి బిహైండ్ ద పవర్ అదే లైక్ పవర్ ట్రాన్స్ఫర్ కెపాబిలిటీ బిహైండ్
forget about power transfer limit and all, you consider this power angle curve.
Okay, 90
we
degrees.
reach to this point. Okay, so 600 megawatt point. Whenever load demand was little increased, speed is increasing. Sorry, motor speed is decreasing. Delta is increasing.
Yeah, power required.
But real power supply is decreasing.
Yes, sir.
Then it's unable to meet the demand.
Okay.
Your motor output is more compared to input.
Okay.
Rotor speed will further fall down.
Then it will out of synchronism and will
That's
stop.
what we did. That's what we said. Beyond 600 megawatt means if you are attempting to transfer a power beyond 600 megawatt in your power network, the network is not allowing, means network is unable to transfer that much amount of power. It is causing for loss of synchronism between two machines.
But you said that PE 5.0 and generator 605.
Generator, you can take 605. That's in your hand, right?
But no need of that, like. And a
Have you
generator
understood
mechanic
this
power.
one? Without this 605, have you understood this one?
Oh, yes, sir.
Okay, I explained the similar thing in two ways. Some people might be understanding this. Some people might be understanding this one.
Okay.
Okay. Some people are saying that, sir, why this power has not increased from 600 to 605? Are you saying that the 600 megawatt is rating of generator? That's the question what arised. Okay.
But
So
no
I
need.
don't have an issue with PS1 value. PS1 value I can increase according to the requirement.
Yes, we can increase, but no need.
I made it in the next slide. I made it from 600 to 605 intentionally. But still your network is unable to transfer. Means my intention is to tell you, generator is okay. Motor is also okay. Network is offering that limit. To explain that one only, I said that 600 to 605 we have increased the mechanical limit.
Okay.
I don't know what's your exact doubt, Kumar. Can you please elaborate it?
Here network means transmission line. Network means transmission line.
Transmission line, that reactances, network of reactances, what you say, between voltage sources.
If that if the design of the network at 600, your design like 600 megawatts.
I have not designed. We have some reactances. We got it as 600.
Okay, sir. Like
okay.
If the motor is capable to behind that, how they know, sir? Capability is behind that. Network.
How they know means network is offering it. How they know means what? Tell me, Kumar.
Sir?
Tell me, please.
Did not get it. Okay, sir, I will think on it. Sir, I have another doubt. That is. Sir, ఇక్కడ synchronous motor is decided, frequency of the synchronous motor is decided by omega m, rotor of the synchronous motor, you said.
Rotor speed, yes.
Okay. Actually, synchronous motor is rotor rotated at ns, because of it is magnetically locked with rotating.
How it is rotating at ns?
It is the operation of the synchronous motor is because of magnetic locking, right?
That magnetic locking only I am saying it is losing.
Even though
that is the point of loss of synchronism, right? If you have magnetically locked, both will have same frequency. Both rotors will rotate at synchronous speed.
So after the angle between the synchronous motor rotor and its starter flux, means rotating magnet flux.
Don't talk about stator flux. Why you are talking about stator flux here? Have I talked about stator flux anywhere?
No, sir, but magnet locking
delta
is different.
Delta is an angular difference between two induced EMFs or two rotors.
Here delta is between generator and rotor.
Okay.
But magnet locking of the synchronous motor is depends upon its rotor and its rotating magnet flux angular difference.
That again you take terminal voltage there. Again, while you are
Oh.
analyzing the motor, you will be taking terminal voltage as constant, right?
Yes, sir.
The terminal voltage is constant means what? It may be infinite bus again.
Okay.
It is again an infinite machine. Means synchronous motor connected to infinite bus bar.
Sir, what I'm thinking is that, sir, can you take the reference as the generator rotor 0 degrees, for example?
Okay, generator rotor 0 degree. Okay.
So easy at an angle of some difference will be there, right?
Easy at an angle 0. You said generator rotor as a reference.
So easy 0, EM also 0.
VM also 0. What is that?
Means EM some okay. Okay, sir. And I got it.
Okay, fine. Any other doubt you have, Kumar?
Any other doubt? Synchronous motor. Sir, normal doubt, like if there is synchronous motor, right? We need if there is brushless DC motors, but beyond that, we need some DC power to the rotor. Hello.
In
Sir?
case of brushless DC motor, you don't have DC power to rotor.
If not BLDC, in olden days we need some DC supply.
Yes.
Sir, the DC supply is taken from the three-phase supply, or we taken some other?
Maybe from battery. They might be supplying the DC.
Some other batteries, not from three-phase
Some
supply.
other battery. But in case of your power station, the DC supply will be taken from grid only. Means from connected AC bus bar only they will take.
Yes, sir.
From that they will
Sir,
convert it to DC and they will apply to rotor winding.
okay. What I'm thinking is that in fault analysis, you said that, sir, synchronous motor, because of rotor flux, there is some, even though fault occurs, EMF induced, right?
Yeah.
So rotor flux present, so rotor flux present, but speed of the rotor slightly decreases slowly.
Speed of rotor we will be assuming as constant in complete fault analysis, right?
Okay, because as frequency constant we take in it, but practically it will decreases.
I don't say it's decreasing. It may increase or decrease. That depends upon the situation. That
Okay,
depends
sir.
upon your initial operating conditions.
Okay, sir. Okay, but here rotor flux is also depends upon supply. So as a power interruption there,
Rotor flux, why it depends upon supply?
we taken from supply.
But you already converted to DC, right?
That will converted from three-phase supply, right?
That's what I'm saying. It's already converted to DC. The DC voltage you are giving as input, right? What's the thing you have to do with AC frequency?
It's not depends upon AC, sir. అంటే AC గురించి నేను ఫ్రీక్వెన్సీ గురించి చెప్పట్లేదు సార్. అంటే ఇప్పుడు రోటర్ ఫ్లక్స్ ఉంటేనే కదా స్టార్టర్ లో EMF ఇండ్యూస్ అవుద్ది. సో రోటర్ ఫ్లక్స్ ఉండాలంటే దానికి సప్లై ఉండాలి. దాని సప్లై అనేది ఇప్పుడు ఫాల్ట్ రావడం వల్ల ఇంటరప్ట్ అయిపోద్ది కదా అనే నా డౌట్. ఓకే, ఒక బ్యాటరీ
what is that gap you have between rotor excitation voltage and AC voltage?
Rotor excitation voltage.
Between that you have a rectifier, right?
Yes, sir.
The rectifier is converting that AC to DC.
Yes, sir.
And how much DC value we need? How much AC input is available to you? AC input voltage available may be very large.
But because of fault, it will drop, sir.
Even though it is dropping, but your DC voltage can be maintained as constant, right?
How, sir?
11 kV fallen down to 1 kV.
Okay, you taken some voltage will be there.
Initially 11 kV, we are getting a DC voltage of, let's say, 500 volts.
Okay.
Means 11 kV three-phase AC voltage we have converted into 500 volts DC. But how much is your firing angle? Very, very low.
Yes.
If it is 1 kV, they might increase the firing angle automatically.
Okay.
They might increase means automatic control will be there to have the control of the firing angle alpha.
Okay. Okay, sir. I'm thinking that voltage completely drop to 0, but might be something.
You have a control, right? You have a control by means of rectifier, right?
Yes, sir.
Automatically, whenever that AC voltage is falling down, that firing angle is going to be changed because of that DC output is going to be maintained as almost constant. Firing angle decrement they will do, not increment, decrement they will do.
So,
Any other doubt here, Kumar?
no, sir.
Yeah.
No, thank you, sir.
Tulsi,
Hello, sir.
tell me, Tulsi.
Sir, 6F, sir.
Okay.
Sir, first sentence ఎలా ఎఫెక్ట్ అవుతుందో ఒకసారి ఎక్స్ప్లెయిన్ చేస్తాను.
Initial point, you take delta not angle. Initial point means this delta not angle you have, na?
ఎస్ సార్.
That angle.
ఓకే, ఇనిషియల్ ఆపరేటింగ్ కండిషన్.
Initial operating point means initial power flow is how much? Is it close to P maximum or far behind the P maximum?
ఓకే.
That definitely decides the system stability, right?
ఓకే సార్. సార్ అలాగే ఈ డెల్టా సిఆర్ యాంగిల్ కి కూడా లిమిట్స్ ఉంటాయా సార్? అంటే ఎంత తక్కువ టైంలో క్లియర్ అయితే స్టెబిలిటీ అంత ఎక్కువ ఉంటుంది అలాగా.
We will discuss in transient stability.
ఓకే.
We are not discussing about fault now. We are
సార్.
discussing about only small disturbances, right?
ఎస్ సార్. సార్ మళ్ళీ ఆ రోటర్ యాంగిల్, రోటర్ స్పీడ్స్ రెండు సేమ్ గా ఉంటాయా సార్? ఇప్పుడు లాస్ట్ లో ఇండక్షన్ కాకుండా అంతకుముందు ఒకటి ఎక్స్ప్లెయిన్ చేసి పేజ్ నెంబరు నెక్స్ట్.
This one.
ఎస్ సార్. ఇక్కడ సేమ్ తో
The
రొటేట్
machines, if the machines are required to be synchronized, both rotors should rotate at same speed.
అంటే ఇప్పుడు 1500 ఆర్పిఎం తో ఫస్ట్ ది రోటర్ జనరేటర్ రోటర్ రొటేట్ అయితే మోటార్ రోటర్ కూడా అదే స్పీడ్ తో రొటేట్
అదే
అవ్వాలి.
స్పీడ్ తో రొటేట్ అయితేనే machines are in synchronism అంటారు.
ఓకే సార్. అప్పుడు డిఫరెన్స్ యాంగిల్ ఎట్లా వస్తుంది సార్ దానికి? అది నాకు
Both are
విజువలైజేషన్.
rotating at same speed does not mean that both are on the same line, right?
ఓకే, నాట్ ఇన్ కోయాక్సియల్ ఫేజ్.
Not in coaxial.
ఓకే సార్.
You have some axial difference between the rotors.
ఓకే సార్.
Okay.
సార్ నిన్న చెప్పిన దాంట్లో అక్కడ ఒక నిమిషం సార్, కరెంట్స్ ఎందుకు జీరో అవ్వవు సార్? అవి మామూలుగా ట్రిపుల్ ఎల్ ఫాల్ట్ లో
Which currents?
ఐఏ ప్లస్ ఐబి ప్లస్ ఐసి గ్రౌండ్ ట్రిపుల్ ఎల్జీ గ్రౌండ్ అవుతాయి కదండి సార్. అప్పుడు ఐఏ ప్లస్ ఐబి ప్లస్ ఐసి కూడా జీరో అవుతుంది. ఫాల్ట్ కరెంట్ జీరో అని రాయం
If the
కదండి సార్.
pre-fault system is balanced, it will be ground current will be zero.
ఎస్ సార్.
If ground current is becoming zero, can you say fault current is zero in your answer?
గ్రౌండ్ కరెంట్ కానీ ఐఎఫ్ ఇస్ ఈక్వల్స్ టు ఐజీ అవుతుంది కదండి
Who
సార్.
said IF equals to IZ? It's not in all cases, right?
ఎస్ సార్. ఎస్ సార్.
It's not in all cases. IF equals to IZ.
ఐజీ. ఓకే సార్.
If ground current is zero, we should not say that ground current as fault current. We should
yes.
call one of the phase current as fault current at that time.
వన్ ఆఫ్ ది ఆ సెంటెన్స్ నాకు అర్థం కావడం లేదు సార్. వన్ ఆఫ్ ది ఫాల్ట్.
See, already you have a fault on the system. That is clear.
ఎస్ సార్. ఎస్ సార్.
If ground current is becoming zero, can you say fault current as zero, even though you have a fault on system?
ఓకే, నో సార్, వీ హ్యావ్ సమ్ ఫాల్ట్ కరెంట్ ఈస్ గోయింగ్. ఎస్ సార్.
That current we should answer at that time.
ఓకే సార్. సార్ అనదర్ డౌట్ సార్. సార్ షార్ట్ లైన్ లాంగ్ లైన్ లో ఫెరాంటీ ఎఫెక్ట్ చెప్పారు కదండి సార్. అది షార్ట్ లైన్ లో కూడా ఫెరాంటీ ఎఫెక్ట్ కాకపోయినా నార్మల్ గా వోల్టేజెస్ ఇంక్రీజ్ అవుతాయి కదండి సార్. మనము 1.732 ద్వారా అట్లా ఇంక్రీజ్ అవ్వవా సార్?
No, we have discussed about the current effect in pre-fault condition, right?
ఎస్ సార్.
After the single line to ground fault has been occurred on an ungrounded neutral system,
ఎస్ సార్.
healthy phases voltages will be equals to √3 times of pre-fault voltage.
ఎస్ సార్.
In case of short line, short transmission line, pre-fault voltage may be 1 per unit.
ఫర్ ఆల్ ద త్రీ.
All the three,
ఓకే సార్.
right? So there you get √3 into 1 means 1.732. That's it.
అది షార్ట్ లైన్ లో ఎందుకు ఉండవు అని డౌట్.
Short line you don't have Ferrand effect, right?
ఎస్ సార్.
See, in both cases, voltage will be increased by √3 times.
ఎస్ సార్.
Either the line is a long line or short line, voltage
Short
will be increased by √3 times.
ఎస్ సార్.
√3 times of what? Its
Pre-fault.
respective pre-fault voltage.
ఎస్ సార్.
√3 times of pre-fault voltage in short line analysis. √3 times of pre-fault voltage in long line analysis.
ఎస్ సార్.
But the pre-fault voltage in case of long line will be higher than 1 per unit due to Ferrand effect.
ఓకే. ఎస్ సార్. అప్పుడు షార్ట్ లైన్‌లో కూడా 1.732 ఇంటూ 1 ఇంకా లాంగ్ లైన్ ఇంకా ఎక్కువ ఉంటది కదండీ సార్.
Yes, that's what I said. We have possibility of getting arcing ground more in long line compared to short line.
ఓకే. ఓకే సార్. అంటే మనం రాసేటప్పుడు అక్కడ జస్ట్ వీబీ, వీసీ కూడా లాంగ్ లైన్‌లోనే 1.732 అని రాసాం అంతే సార్.
There also, if you want to write, I have not
Okay.
written in short line. If you want, you can
Okay.
write it.
ఓకే.
Okay.
గుడ్. ఓకే. థాంక్ యూ సార్.
Shiva,
Hello, sir.
tell me, Shiva.
Sir, at 21 inch, sir.
Okay.
Sir, here you said that the generator axis leads, the motor axis. So why is it so?
In which direction that real power is flowing? Generator to motor, right?
Okay, sir.
Then according to your power equation, generator induced EMF will be in leading with respect to motor induced EMF.
Means
For example,
generator
you see
is
this
supplying and that's why we have a lead.
Look here. If you see this one, P equals to mod E mod V by X equivalent into sine delta, right?
Yes, sir.
If the delta is positive, then P is positive.
Okay, sir. Got it, sir.
Okay.
Yes, sir.
So
Sir,
in that
then,
way, if you have a positive power flow in the sense, obviously generator rotor will be in leading compared to the motor rotor.
yes, sir.
Then only we have a power supply from generator to motor.
Yes, sir.
Quickly, we should say in a reverse way. As we have real power flow from generator to motor, generator induced EMF will be in leading with respect to motor induced EMF.
Okay, sir.
That's a statement you should say. Okay.
Yes, sir. Sir, and then one more thing, the power angle curve, what we discussed here is for a lossless system, right, sir?
Lossless systems.
So then in practical networks, we have losses also.
There is a shift in the power angle. If we have some power loss, small shift you get in the power angle curve.
So that is the only difference we can experience in
That's only the difference. But you don't get that 90-degree concept there. You will have some other angle.
Okay, sir.
You may not have 90-degree, you get some other angle.
Okay, sir. Sir, and
Okay.
then 600 megawatt case, sir, around 30 or something.
Yeah.
Sir, here.
Tell me.
Sir, here the increase in or the change in PS2 depends on the network, something you said, no, sir.
Change
I
in
mean, the change in PS2 value, it was decided by something.
PS2 is in our hand.
Okay, sir. So the
Change in
maximum
PS1.
transfer.
Listen, change in PS1 also in our hand.
Okay, sir.
But real power flow in the network is not in our hand exactly.
Yes, sir. That I was.
Okay. Tell me, what's your doubt?
No, sir. Here, so both PS1 and PS2 changes in our hands only.
Yeah.
Okay, sir. Okay. Yes, sir. That's it, sir.
Okay.
Yes, sir. Thank you, sir.
Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, I sent you on doubts at that one only.
What is that? Please tell me.
I sent you a question, sir, in Telegram afternoon.
Read it once.
Sir, that is Delta connector network, sir.
Okay.
Unbalanced supply from it is feeding, sir.
I think already we solved that question in class.
Sir, I searched, sir, but I didn't get. Sir, so once you say,
Not
sir,
in last year lectures. This year lectures we have solved, I think. You attended last year also, right?
Yes, sir.
This year lectures we solved, I think.
Okay, sir. Sir, there how to find IB, sir?
Phase B current. Some of the
Yes.
three currents is 0. IA plus IB plus IC equals 0, right?
Yes, sir.
Because there is no path coming out.
Sir, can't we do what I sent, sir? Means IA will be divided into two resistors equally.
How you can do that current division? You can't do, right? Between them.
Sir, that means they equally resistor, no, sir. Equal impedance.
Still, how you can do that current division? When we can do current division between two elements?
Yeah.
If and only if those two are in exactly parallel.
Yes, sir. Okay.
But those two are not in parallel, right? Two resistors.
Yes, sir. Okay.
So you should not do current division.
Okay, sir. Okay, sir.
Okay, Pratyush?
Yes, sir. Thank you, sir.
Yogashri,
Sir,
tell me, Yogashri.
sir, 28F and 30F, what is the difference, sir? And
Both are same only. Which you have understood clearly, both or anyone?
Sir, two same ఉన్నాయి కదా sir వాటిలో.
Same. Have you understood both?
Sir, synchronous mode అంటే ఇక్కడ మోటార్ PM ఉంది కదా sir ఇక్కడ.
1 minute. Tell me, what is it?
సార్ ఇక్కడ మోటార్ దగ్గర మెకానికల్ దగ్గర ఇప్పుడు ఇంక్రీజ్ అయితే ఇక్కడ పవర్ సప్లై ఉంది కదా సార్ ఇక్కడ S1 PS1 కూడా ఇంక్రీజ్ అవుతుంది అనేసి అన్నారు కదా సార్.
That we have taken as assumption in the previous case. But in this case, what I am saying is, according to changes in the electrical power, this mechanical input is changing.
Okay.
Okay, two different scenarios we have seen. That's it.
సార్ ఒకవేళ ఇక్కడ ఫాల్ట్ వస్తే ఏమవుతుంది సార్?
Fault we will discuss later. Why you have doubt now? Fault. Where we have fault? Tell me, Yogashri.
అంటే ఈ లైన్ డయాగ్రామ్ లో ఫాల్ట్ అనేది అక్కర్ అవుతే
Then electrical input to the motor is 0.
P is 0 na sir?
P equals to 0. Yes. Then
Both
electrical
cases,
power
sir.
output of generator is 0.
Okay. So both cases 0 na sir?
Yeah, both sides it will be 0.
30 slides, 30F slide and 20F slides diagram is it? Both ekkada diagram lo vachina fault 0 P equal to 0 indulo vachina P equal to 0 na?
Yes, in any case.
Okay sir.
Same network, right?
Okay sir.
Then how is your PS1, PS2, whether PS1 is varying, PS2 is varying, that decides the rotor speeds.
Okay sir.
Understood, Yogashri?
Yes sir. ఒకవేళ అసింక్రనస్ మోటార్ అంటే రెండు సేమ్ కాకపోతే వచ్చేసి అసింక్రనస్ మోటార్ అవుతుంది సార్.
Tell me please again.
సార్ సింక్రనస్ మోటార్ అంటే రెండు ఈక్వల్ ఉంటేనే కదా సార్ రోటర్ స్పీడ్ అనేది ఈక్వల్ ఉంటేనే కదా సార్ సింక్రనస్ మోటార్ అంటాము.
Okay, speed is constant with respect to time. Then we call that
Yes,
a
sir.
synchronous motor. But whenever you have a disturbance, it is not sure to say the speed is constant all the time.
Okay.
Speed may come back to constant speed.
Okay.
After creating disturbance and after some time, the speed may come back to synchronous speed.
Okay.
For
sir.
example, you have increased the load on the synchronous motor.
Okay.
Speed will decrease definitely.
Yes sir.
But after some time, it will come back to synchronous speed. Hence, the motor is called a synchronous motor.
Okay sir.
But in case of induction motor, whenever you increase the load, the speed may not come back to the original speed again.
సార్ ఈ కేసులో
We end up with a
అసింక్రనస్
different
ఎలా
speed.
ఉంటుంది? ఈ కేసులో అసింక్రనస్ మోటార్ ఎలా వస్తుంది సార్?
Asynchronous motor, what is that?
అంటే సార్ ఇప్పుడు కాన్స్టెంట్ లేకపోతే అప్పుడు వేరీ అవుతుంటుంది కదా సార్, అప్పుడు అసింక్రనస్ మోటార్ అనొచ్చా అంటున్నాను సార్.
No, you should not call it.
ఓకే.
But synchronous motor, asynchronous motor, that we will say in the way of steady state operation,
ఓకే సార్.
not in this simple transients. Simple transient.
ఓకే సార్.
Any other doubt you have, Yogashri?
నో సార్.
What do you mean by synchronous motor? Tell me.
So constant speed, it's a variable by time.
Is it always constant speed?
No sir, it
No.
sometimes
When
it will
it
be
will vary
decrease or
speed?
increase. Sir?
When the speed will increase or decrease?
It's a load
Whenever there is a disturbance on load side or
disturbance, sir.
disturbance on the network, speed of the motor may change.
Change. Yes, sir.
If it is coming back to synchronous speed again, means coming back to the same speed of original, I will say that motor is synchronized with the system
Okay, sir.
and it is stable.
Nice, sir.
If it is not coming back to its original speed, definitely speed will vary continuously and it will be unstable.
Okay, sir.
That is synchronous motor. In case of induction motor, what will happen? Whenever you add some load or delete some load, speed will change and it won't come back to the original speed.
Okay, sir.
Even though it is not coming to original speed, still it is supplying its own load.
Okay, sir.
Okay?
Okay, sir.
Yeah.
Sir,
Tell me.
సార్ ఇప్పుడు ఫాల్ట్ అక్కడ అయితే ఇక్కడ ఎలా క్లియర్ చేస్తాం సార్ ఫాల్ట్?
I have not shown any breakers, right? If you have breakers, it will clear the fault.
ఓకే, ఇప్పుడు అంటే బ్రేకర్స్ లేనప్పుడు ఫాల్ట్ వస్తే క్లియర్ చేయలేం కదా సార్?
That's why we are keeping breakers, right, Yogeshri?
ఓకే, అంటే ఈ డయాగ్రామ్ లో ఫాల్ట్ వచ్చినప్పుడు బ్రేకర్స్ పెడతామేమో కదా సార్? అంతేనా?
You think in the designing way, Yogeshri. We have taken
సార్,
up
అదే
from
ఇప్పుడు ఈ
paper.
లైన్ డయాగ్రామ్ లో ఫాల్ట్ అక్కర్ అయినప్పుడు ఇప్పుడు మనము బ్రేకర్స్ అనేది పెడతామని అంటున్నాను సార్. ఆ డిజైనింగ్.
When you will keep after the occurrence of fault?
No, before the occurrence of the fault, by designing only, sir.
That's it. That's it. We should design that protective switch gear according to the requirement.
Yes, sir.
Then after the fault has been occurred, the breakers will open.
Okay, sir.
Okay?
Okay, sir.
Yeah. Anil Kumar.
Sir, good evening, sir.
Good evening, Anil.
Sir, in 5F.
Okay.
Sir, in this, we can decide the input based upon that controlling valve, sir, which is constant or that like, sir, but output we can decide. That point we can explain again, sir. That electrical power, whether it is
output
constant
depends
based.
upon your physical system, right?
Yes, sir.
That energy storage, energy discharge, all these things will decide it.
Okay, sir.
But if it is a stable system for you, electrical power output also becomes constant after some
Okay,
time.
sir. Okay, sir.
Right? As we say, delta is constant with respect to time, electrical power output also constant with respect to time.
Okay, sir.
But if electrical power is continuously varying something like this, then we will say system is unstable.
Understood. Okay, sir. So, but we can control the input based on our load demand.
You can control it. How to sense that load demand?
So, based on our rotor speed.
Again, based on frequency only. It will sense the load demand again based on frequency.
Sir, that infinite bus, how we can conclude that frequency is constant, sir?
Even you connect a load or disconnect a load, or connect a generator, disconnect a generator, that bus voltage and frequencies are not changing, right?
Oh, yes, sir. Okay, sir. Okay. Even a large.
It is called as infinite bus.
Okay, sir. Okay. Yes, sir. I understand, sir.
Yeah.
Thank you, sir.
Any other doubt, Anil?
No, sir. Thank you, sir.
Fine. Bharat.
Hello, sir.
Tell me, Bharat.
Sir, initially we considered the Indian power system network as an infinite bus, no, sir? And at last you said, while asking a doubt, some person, at that time you said like the big network can be represented as synchronous motors, sir. So how is that?
Infinite bus means what?
Voltage and frequency will be constant.
Okay, how you are modeling it? Are you modeling this as synchronous machine?
Sir, we don't have reactance.
Okay, but still it's a synchronous machine, right? Voltage source.
Oh, okay. So without like while in the analysis, so we consider it as a synchronous motor because
it is drawing means why it is synchronous motor means because whatever the power you are injecting, it is taking. So it will act as a motor.
Okay, so like the reactance that we don't need to bother about that.
No need to bother about it. If it's a voltage source, it is sufficient to say.
Okay, that's it. Thank you.
Imtiaz.
Good evening, sir.
Good evening, Imtiaz.
Sir. Hello.
Tell me, Imtiaz.
Sir, could you explain that one 600 to 590 megawatt? Is there no?
Okay. What's the doubt you have in this?
I understand through that curve, sir. But you said no one.
From curve only
statement.
we are saying this one, no? I'm in charge.
Yes, sir. But you said no one statement. Kinetic energy stored in the rotor. Could you tell that I will write, sir?
See, output energy is more for the motor. For motor.
Yes, sir.
Output energy is more, but input energy is less.
Yes, sir.
So to meet the excess output, the stored energy in the rotor has to be supplied to the output.
That's true. Sir?
The stored energy in the rotor should be supplied to meet the output.
Okay, sir.
Then motor speed will decrease further.
Okay, sir.
Delta will increase further.
Yes, sir.
Input energy will decrease further.
Yes, sir.
Then to meet the more output, again kinetic energy will decrease.
Yes, sir.
Then omega further decreases.
Okay, sir.
Delta further increases.
Yes, sir.
Electrical power further decreases.
Okay.
And the cycle will continue up to the point when we reach the speed equals to 0 in the motor.
Okay.
Understood?
Yes, sir. Sir, one more is there.
Tell me.
Sir, I solved one problem in the workbook, sir. It's saying that tie bar is connected to a tie bar, means, sir?
Tie bar means it's a different type of reactor connections.
Means T type, sir?
Not T. I'll tell you. It is this type of connection actually. Tie bar means it is one generator. Okay. And it was second generator.
Okay, sir.
Okay. So, and from this, we will be connecting one reactance. And this is going to be called as tie bar. Okay.
Okay, sir.
And from this bus, you have the load supply. In this. For example, if we add one more generator here, connected to this, which is called as tie bar.
2 or 3, more than 2.
More than 2, whatever. More than 2 or 3, 4, whatever it is. These are these reactances you have, na?
Yes, sir.
These reactors are called as tie bar reactors.
Okay, sir.
Okay.
Yes, sir.
Any other doubt here?
No, sir. Thank you so much.
Yeah. Anybody having doubts? Please raise your hands. Anybody have a doubt? Please raise your hands. Okay. Thank you. I think nobody is having a doubt.
Sir.
Tell me, Imtiaz.
Sir, I will read that question, sir. Could you solve that problem, sir?
Which one?
That's a tie bar problem.
Yeah, you calculate it. I think they have given 15% reactance of tie bars.
Yes, sir. You have to
Each
only
one will have 15%. Generator reactance is given.
Yes, sir.
And they will ask you to find out short circuit MVA. At what location? At any one generator terminal.
Yes, sir. You have said the two alternatives, sir.
Yeah, you connect in this manner and find out the short circuit capacity at some bus bar, means at this place, by finding out X equivalent.
Okay, sir.
Okay,
Sir.
you do that and send solution to me.
Okay, sir. I send in Telegram one.
I will check once. Okay.
Hello, sir.
Okay, sir.
You do the solution, Imtiaz.
Okay, sir.
You do the solution and send solution to me.
Sir, I send one transformer related that the neutral point, sir.
I will see once. I will see and I will let you know.
Okay, sir. Okay, sir.
Okay.
Thank you so much, sir.
Okay.
Sir,
Tell me, Yogeshri.
సార్ ఆఫ్లైన్ లో ఉన్న వాళ్ళు ఇప్పుడు కంటిన్యూ చేయొచ్చా సార్ ఆన్లైన్ లో?
That you ask the concerned person. You ask once.
Okay, sir.
Okay. You have those numbers, right? Contact numbers, right?
Yes, sir.
You inquire once. Huh?
Okay, sir.
Bhavin.
Hello.
Tell me, Bhavin.
Sir, I have doubt in 7F, sir.
Okay.
On this, sir, you draw one network, sir, and you said that there is if there is a fault, if there is a fault, sir, the circuit breaker will operate, sir.
Yeah.
And sir, if circuit breaker operates, sir, after some time they will take trial if the fault is clear, sir.
Yeah.
Sir, if fault is not clear, then that line will be isolated. No?
Yes.
Sir, if that line is isolated, then there will be change in the load. So will there be any effect on the generator?
That's what we are studying, delta variation.
So only that will happen. Other than that, nothing.
Other than that, nothing means if system is stable with respect to delta, it will be stable with respect to remaining two also, right?
Sir, but in case of induction motor, it is not happening. No?
Induction motor?
Sir, in case of induction motor, there is no delta. So only we are studying. So sir, I'm little bit confused in this, sir.
Then you study only about mod V at that time. This rotary angular stability concept will come if you have two or more number of synchronous machines, I said.
Yes, sir.
If you have only one synchronous machine, then you no need to study about angle. You study about only magnitude of voltage variation.
Okay, sir.
Then there's no concept of frequency stability and delta stability, right? You have only mod V stability.
Yes, sir. Yes, sir. Okay, sir. That's it, sir.
But for example, if it's an induction motor to you, tell me, do you do angular stability for the system or not?
No, sir. In this case, we are not doing.
Why?
Only VNF. Because there is no load angle in induction motor.
Two synchronous machines are there, right?
Yes.
What you have understood, Bhavin?
Okay, sir. If only one generator is there and
yes.
the other is
you have
not
only
there.
one generator, only one synchronous generator, no rotary angle concept.
Okay, sir. Okay, sir.
But here you have two synchronous generators, right?
So we will do total triangle study.
Yes, yes. Yeah.
Thank you, sir.
Tulsi.
హలో సార్.
Tell me, Tulsi.
సార్ ఆ టై బార్స్ ఒకసారి ఎక్స్ప్లెయిన్ చేస్తాను.
Tie bar connections will be in this manner.
ఓకే సార్.
Anybody says that we have a tie bar reactor, we should connect one reactor from this bus bar, and all these tie bar reactors, one end will be connected, joined together.
Okay, sir.
Okay, and this bus bar, generator bus bar is supplying power to feeders.
Yes, sir.
Okay, these tie bars are used in this interconnection to reduce the fault level as we have studied earlier.
Yes, sir.
Okay.
Yes. That's all. Thank you.
Sai Charan, do you have any doubt?
Sir, in yesterday's reactor problem, sir, when we connected circuit breaker near the generator after the bus bar, sir.
Okay.
You told that if the fault occurs, then the rating of the circuit breaker will be according to the greater current.
Greater current.
But if the fault occurs Sir, can you take a fresh space, sir? I
Tell me.
cannot. I'm not able to explain.
Tell me, Sacharan.
Sir, in yesterday's class, after analyzing CB1 and CB2, you wrote CB3 and CB4, na, sir.
This is CB3.
Yes, sir. Yes.
This is CB4.
Yes, sir.
Now, what you have to do is you take fault at this location. Find out current from this side. Current from this side.
But fault will be not exactly on that point, na, sir.
You remove the breaker and take the point, Sachiran.
Okay, sir. Sir,
Remove the breaker. Remove the breaker.
Okay,
Take
sir.
the point.
Okay, sir. So I'm confused that if the fault occurs between circuit breaker and alternator, then
You take
one current
this
will
fault
be
if you
bypassed.
want. You take this fault. Then this current is flowing in the breaker, right?
Yes,
That
sir.
is 1 per
But,
unit.
and yes, sir.
This is 0.5.
This 0.5 circuit, 0.5 current will be bypassed to fault, na, sir.
Fault.
It will
It
not.
won't flow in the breaker.
So now no need of taking highest one of those.
I don't say a fault is going to occur only on this side. It may happen on the other side also, right? So you take fault on this side. Then what? 1 per unit will not flow in the breaker. It will be going into ground. Means fault. 0.5 will flow in the breaker.
Yes, sir. Yes, sir. So,
Then you should say maximum of the two.
yes, sir. So I thought that at the fault condition only, but we will assume the worst condition of that both of them.
Worst condition of two sides.
Yes, sir. Yes, understood.
Yeah.
Sir, can we say that tie bars are also called as reactors?
Tie bar reactor it is. It's an interconnecting reactor. It's a tie bar reactor.
Okay, sir. Interconnector reactor means connecting the two bus bars, but tie bar means individual bus bars are connected.
There is another bus bar formed here, na?
Yes, sir.
It is going to be called as tie bar.
Okay, sir.
Okay.
There will be a common point.
Common point between all reactors connected.
Okay, sir. Okay, sir.
Okay.
Oh, yes, sir.
Yeah. So, see, do you have any doubt more?
No, sir.
Yeah. So, anybody have doubts? Please raise your hands.
Sir.
Tell me, Anil.
Sir, in per unit system, I have doubts. Sir, in one of the question, in solving a fault analysis by neglecting the static load means we have to modify the formulas of per unit new, sir.
Oh, static load.
Sir, they have mentioned that for fault analysis by neglecting the static loads means we have to modify.
Static loads are neglected means they don't consider the fault current supplied by the static loads. That's the meaning.
Okay, sir. We have to neglect that kVA base old by kVA base new, sir.
You are talking about that now. kVA base new by kVA base old. Means you are saying me I no need to calculate jet per unit new for static load, is it?
Yes, sir. They are not calculating that kVA base old by kVA new, sir. They have mentioned that exactly Z per old into MA base new by MA base old.
That's okay. That formula is okay. What's the relation between that formula and your doubt now?
Whether I have to consider that kVA base old by kVA new, sir.
Why you have to consider?
Sir, I am asking, sir, suppose they have.
What's your doubt, Anil? What's your doubt? Please explain
Sir,
clearly. What's your doubt?
Sir, in this question, they have mentioned that fault analysis by neglecting the static loads. They have mentioned.
Fault analysis by neglecting the static load means simply you throw that static load out and you do fault analysis on the remaining network.
Okay, sir.
That's it. Means you no need to do any calculations of static load impedance and all.
Okay, sir.
Calculate the remaining part of network impedance only and you do fault analysis.
Okay, sir.
Okay?
Sir, in another question, as we solved in a class, suitable location, we have to choose base rating, sir, new base rating. Sir, likewise, we are choosing first generator, transformer, and overhead lines, sir. Afterwards, overhead lines, they are connected to generator parallel, sir. As they were mentioned that before overhead lines, they were mentioned that KVA has been, we have to consider, no, sir, new we have to
At any
calculate that.
location, you can take the base, Anil.
Oh, okay, sir.
It's need not to be at the generator. At any location, you take the base and transform the base values in a proper way from one to the other.
Okay, sir. Okay.
That's it. It's no need to start only from generator. You can start at any point.
Okay, sir.
Okay.
Okay. Thank you.
Any other doubts? So I think we can leave for this day. Thank you.